Night rises in layers when a telescope is given time to breathe. Detectors settle into quiet, mirrors release the last warmth of day, and the dome becomes a pupil that drinks the sky. In that hush, the universe is not a spray of stars, but a tide that drifts outward without shore. Somewhere within that tide, gravity folds light back upon itself. Photons that have voyaged for billions of years encounter a frontier where forward and inward become the same direction, a one-way slippage into a region sealed from the rest. This frontier is not a surface that can be touched. It is a boundary traced by equations that speak in the language of curvature and causality. It is the event horizon, the skin of the abyss, the limit past which all stories become interior monologue told to a silence that never replies. Hearts are set beating by difference. Flames rise because heat is uneven. Rivers run because height is not the same everywhere. The cosmos, too, moves because gradients exist, and gravity expresses those gradients as warps in space-time. In the deepest wells, the warp becomes absolute. No path leads back out once crossed. A black hole is the completion of that logic, the final syllable in gravity's sentence. It is not so much a thing as an instruction written into geometry. Mass and energy dictate how space and time bend. Space and time dictate how matter and light must travel. In that closed circle, a solution emerges where the bending becomes total. Space curves inward so completely that all roads end at a central place that does not have a place. A singularity described by the mathematics of the Schwarzschild solution for a non-rotating case or the Kerr family for a spinning one. It is a core where known physics buckles, and yet the horizon it wears is strict and elegant. A radius falls out of the math that scales with mass, the Schwarzschild radius, assigning an austere outline to the unseeable. The night knows these outlines by their effects. Stars near the frontier move as if answering to a conductor that cannot be seen. Gas falls inward and brightens with fury. The darkness is rimmed by its own undoing, a theatre of light created by matter that struggles to remain itself. That light is not merciful. It is the glow of temperature measured in millions of degrees. It is the shriek of magnetic fields combed into order by rotation. It is the whine of infalling orbits that crowd tighter, like notes spiraling into a higher pitch, not because time accelerates, but because energy must be shed to cross the last stable path. The closer it comes to the boundary, the more radiation it spills, and the more vividly the black heart announces its presence without ever revealing its face. The abyss is patient. It gathers, it waits, it drinks. It is also swift when chance brings a feast. A star wanders near and is tidally unspooled into ribbons. A cloud drifts too close and is stirred into a hot spiral that flares before its final descent. Sometimes entire galaxies collide, and their central wells approach like dueling storms, space itself trembling as horizons braid and become one. In each case, the abyss does not move with purpose. It does not plan. Gravity requires no intention. The terror is that indifference can be absolute and still feel like fate. The edge of this gravity is not silent in every sense. To a distant watcher, clocks near the horizon seem to slow, each tick stretched into a longer breath by gravitational time dilation. Light climbing from that slope reddens, wavelengths pulled longer by the struggle upward. There is a visual hush, a dimming and a drift to crimson, as if the cosmos itself were inhaling and holding the breath. Yet for the matter that crosses the threshold, there is no pause. Local physics remains smooth at the horizon. No cliff is felt, only a continuation of descent in a geometry that keeps its final destination hidden behind an unbreakable secrecy. The paradox of apparent stillness and unstoppable plunging is a signature of this edge, an instruction to think carefully about what reference frames mean when gravity writes the stage directions. The blackness is not pure. In the presence of spin, space is dragged around, a slow whirl that compels everything to turn with it. This frame dragging is not metaphor. It is a measurable twist in the way orbits behave and jets are launched. The region where no observer can stand still, even in principle, has a name that sounds like breath meeting metal: the ergosphere. There, energy can be mined by clever trajectories, and the black hole can be made to yield a portion of its rotational hoard. The abyss holds to its rules with severity, yet offers loopholes at the margins, a reminder that extremes carve narrow paths where counterintuitive effects become useful. Terror does not live only in destruction, it lives as well in scale. Supermassive black holes sit in galactic centers with masses equal to millions or billions of suns. Their horizons could swallow the orbits of worlds. Their influence extends outward to fix the rhythms of star formation and the direction of interstellar winds. Younger companions, stellar mass black holes, haunt the galaxy in numbers that remain an estimate, the remnants of collapsed stars that failed to halt their fall with any known pressure. There are also intermediate possibilities, neither stellar nor supermassive, still elusive in census, but increasingly suspected wherever dense star clusters grind toward collapse. All are iterations of the same geometry wearing different sizes. All are depths measured by the same unitless logic of curvature. There is a kind of poetry in the edges, carved by light around these wells. Gravitational lensing bends paths into mirrored arcs and rings. A photon that skims the horizon can loop more than once before escaping, creating nested apparitions in principle, a hall of bright echoes that encircle the void. If eyes could resolve those echoes, the view would resemble a halo built from the stubbornness of light to obey the long curve and yet survive it. On scales reachable by current instruments, that halo blurs into a crescent shaped by motion and beaming, bright on the approaching side, where material swings toward the observer, and dim on the receding side, where light is dragged away. The aesthetic is not an ornament. It is a map of velocity, temperature, and orientation, a painting where each brushstroke is a geodesic. Even in such clarity, the abyss resists personification. It is not a villain, it is not a mouth. It is a region where the fabric of reality permits no return. The imagination struggles because minds are trained on surfaces and shapes, on objects that bear identity, independent of the stage beneath them. Here, the stage writes the play, and the actors cannot rebel. A black hole is the stage sharpening into a trap. The shapes it wears are worn by its environment. The violence belongs to what it consumes. The core remains uncolored by these episodes. It persists as a definition enforced by curvature. Fear grows not from gore, but from recognition that certainty stops. Where complexity grows, where countless interactions pile upon one another, the universe often reveals deeper patterns. In this depth, the pattern ends abruptly. The mathematics says there is a place where density becomes undefined and space cannot be extended in a way that preserves the rules. That is a formal way of saying there is an end to prediction. Perhaps new physics will heal the interior, trading singularity for finitude. Perhaps quantum gravity will stitch together a different center, a gentler microstructure that saves determinism at a cost of intuition. Until that story is written, the horizon stands as an honest perimeter of knowledge. Outside, the night continues, indifferent yet nurturing, cold yet luminous. Galaxies wheel, nebulae bloom, planets tilt under the weight of seasons. Inside, the abyss tightens its hold on whatever passes the line. The two domains coexist, separated by a boundary with no thickness. The image is hard to savor because it asks for awe without comfort. Yet the cosmos has always asked for that exchange. It grants vistas and withholds explanations. It offers laws and enforces them to their end. In the end, the abyss at the edge is not an interruption. It is a completion. The darkness is not an absence. It is a presence articulated so perfectly that it cannot be improved, only approached, only circled by the long pilgrimage of light. A story came to focus when a bright speck near Virgo refused to behave like a star. The night of patient measurements at Palomar gathered a spectrum that should have been familiar. Hydrogen lines, the alphabet of cosmic gas, appeared where they did not belong. The offsets were enormous. The observer who set the prism and read the plates, Martin Schmidt, realized that the pattern matched a star's signature only if the object sat billions of light years away. That meant a power output beyond any known galaxy, a lighthouse blazing with an appetite too great to fit in ordinary narratives. The catalogue called it 3C273. The name was unromantic. The shock was not. Years just before and after that moment felt like a door opening. Radio dishes had already mapped whispers from beyond the Milky Way. A lunar occultation of another source pinpointed a place in the optical sky. The match to a faint star invited a trick of identity. It was not a star, it was a quasi-stellar radio source, soon shortened to quasar. The term carried the strangeness with economy. Lines were broad. Variability was quick. Colors were excessive. Every property argued for a compact engine wrapped in gas moving at a significant fraction of light speed. A few light days of change in brightness demanded a size of the same order. Immense luminosity, issuing from a region smaller than a solar system, required gravity to be doing work on a brutal scale. Evidence collected across the spectrum. In X-rays, the sources burned with surgical intensity, as if a scalpel had been heated white and drawn across the void. In radio, they threw out jets that traced the magnetic skeleton of space. In optical light, they wore crowns of emission from ions that had been stripped and heated until chemistry no longer held meaning. The more carefully observers measured, the more impossible these objects appeared under normal stellar power. Nuclear fusion could not deliver such brilliance from such a small stage. The mind searched for an alternative that did not collapse into fantasy. An answer waited within a theory that had matured quietly. Gravity, when written by Einstein's hand, admitted a solution where space could be so deeply curved that nothing leaving the interior could ever return. Oppenheimer and Snyder had sketched how a massive star might fall through its own horizon. Wheeler had given the solution a single, memorable name. The quasar needed a heart, and that heart had to be a black hole with a mass unlike the remnants of ordinary stars. The bridge between equations and the guilty engine was proposed with modest words and great consequences. The central furnaces of these brilliant points were not burning, they were accreting. They were turning potential energy into heat with a ferocity that no fusion core could match. Astronomy is not satisfied by words alone. The field began to weigh the engines indirectly. Virial methods linked the widths of emission lines to the speeds of clouds dancing close to the source. Reverberation mapping timed the echo between fluctuations in the continuum and the response of the lines, distilling a radius from the delay. Masses emerged from these dances with values counted in millions and billions of suns. The compactness remained, the power remained. The only consistent architecture placed a disk of inflowing gas around a massive hole and let viscosity do the rest. That disk, threaded by magnetic fields and stoked by turbulence, heated to extremes and emitted copiously as it spiraled inward toward the last stable orbit. Sky surveys expanded the census. Wide-field cameras trawled for points with the right colors. The Sloan Digital Sky Survey turned its gaze to vast swaths and returned thousands of candidates with ready spectra. Redshifts piled up on the high end, each one a clock turned back toward the first billion years after the beginning. Some sources arrived from epochs when the first large galaxies were only assembling. Their masses were already in the billion range. The puzzle sharpened into a timeline problem. How could such bulk grow so quickly within the allowed time if feeding rates were capped by radiation pressure? The discovery phase brought not only wonder, but a deadline for theory. Instruments grew bolder. The Keck telescopes watched from a high desert where air thinned and starlight steadied. The Very Large Telescope Array on another dry ridge carved details from spectral forests, crowded with absorption. Space observatories lifted above weather and atmosphere to see wavelengths that ground-based mirrors could only dream about. Chandra found pinpricks of violent X-rays in places where optical light had been snuffed by dust. XMM catalogued long lists of active nuclei, each one a ledger entry in a growing economy of inflow. The Hubble Space Telescope resolved host galaxies around some quasars, revealing tidal tails and scars that hinted at mergers. The story of monstrous hearts needed companion stories about how galaxies feed their centers. Closer to home, quieter cousins signaled the same architecture at lower power. Spiral bulges with bright nuclei showed broad lines and flickering cores. The word Seyfert, from a careful cataloger of unusual galaxies, joined the conversation. Radio galaxies with twin lobes and bright central points, seemed to be kin to the compact objects now understood to be nuclei at different angles and in different costumes. The unifying picture, christened active galactic nuclei, positioned many varieties on a single stage, with orientation and obscuration as the stagecraft. The engine did not change, the view did. Occasional natural laboratories allowed exquisite mass measurements. In a nearby galaxy, maser spots traced microwave emission from water molecules orbiting close to the central mass. Very long baseline interferometry drew orbits with geometer's precision. The enclosed mass left no room for a dense cluster of dark stars or a swarm of neutron remnants. The numbers forced a single object, far smaller than its Schwarzschild radius would suggest for such enclosure. The argument settled on a supermassive black hole as the only tolerable occupant. In the distant universe, the first generations of quasars glowed through a medium that had not yet fully cleared. Spectra showed the fingerprints of neutral hydrogen along the way. Absorption troughs mapped the state of cosmic dawn, when the first lights ionized the fog between galaxies. Each spectrum was both a biography of a single engine and a weather report from the young cosmos. The combination lifted discovery beyond the thrill of a new class and turned it into a probe of conditions that no local laboratory could simulate. The beacons were not just terrifying in what they were generous in what they revealed about everything they illuminated. Newer eyes tuned to the infrared pushed deeper. They hunted the reddest, faintest candidates hidden behind the stretching of light by expansion. Confirmation required patience and coordination. Photons traveled in bands where the air is difficult and the terrestrial night is stingy. The payoff arrived as an inventory of supermassive engines shining when the universe was only a small fraction of its current age. Each confirmation pressed the clock further back, tightening the gap between seed formation and billion solar mass adulthood. The questions that followed did not dim the initial astonishment. They enriched it. Radio interferometers measured jets with unprecedented sharpness. Polarization traced magnetic fields and their wrenching of plasma into alignment. Knotty structures moved along the beams with apparent speeds that exceeded light because geometry and timing conspired to create illusions of superluminal motion. These illusions were not lies. They were proofs of narrow angles and enormous speeds. Every knot and twist tallied the extraction of rotational energy and the conversion into directed fury, a separate but allied clue that the central engines spun rapidly and worked hand in glove with magnetic fields. Catalogues grew thick. The sky became a spreadsheet filled with redshifts, fluxes, line widths, variability indices, and flags that labeled some objects as broad absorption line quasars with winds so strong they ate their own light. The human mind, confronted with abundance, did what it always does. It sorted and sought patterns. A relation emerged between the mass of the central object and the velocity dispersion of stars in the bulge around it. The monster in the middle and the quiet swarm of old stars kept step together as if they shared a common upbringing. Discovery had spilled over from the glare of the nucleus to the architecture of the entire galaxy. The first images of dark hearts could not be taken in the optical, yet an appetite for silhouettes grew. Interferometers stitched globally separated dishes into a single eye, with resolution to approach event horizon scales for the nearest giants. The ambition itself was a form of discovery. It required clocks that agreed to fractions of a wavelength at continents' distance, and algorithms that could reconstruct a shadow from sparse baselines. Even before that goal produced a portrait, the preparation taught the community how to see with a planet-sized instrument. Each calibration and each night of benign weather was a quiet step toward a vision that had once sounded like metaphor. The narrative of discovery was therefore layered. A faint point split into a spectrum. A spectrum hinted at distance. Distance drove luminosity into the absurd. Absurdity demanded a new engine. The engine invited measurements that returned masses that matched the demand. Instruments multiplied and refined the view. The earliest epochs supplied examples that challenged timelines and seeded new theory. The nearby universe provided precise weightings that closed loopholes for alternative explanations. At every turn, the same simple idea remained enough. Gravity could make light fail. If enough mass gathered tightly enough, the failure would become permanent and dramatic. If fuel surrounded that failure, the last light of matter would flare as it lost its identity. The awe that began with the misbehaving spectrum near Virgo did not fade. It broadened into a recognition that the cosmos had written a common script for the cause of Sirius galaxies. Some scripts were quiet and content to smolder. Some erupted with jets that crossed intergalactic real estate. Some announced themselves early in cosmic time with voices far too loud for their age. Each one belonged to the same family. Discovery was not a single gasp. It was a long breathing in of evidence until the picture clicked and remained. What the eyes now expect when looking into a luminous core is a gravity well so steep that even light needs a plan to escape. Rules in astrophysics act like guardrails on a mountain road. They do not erase the chasm, they simply keep the traveler from drifting into it. The shock of the largest black holes is that they lean against those guardrails with a steady pressure that suggests the road must be wider than believed. Growth is the first contested rule. Light produced by falling gas pushes outward on the same gas that feeds the hole. At some brightness, the outward push balances gravity. That threshold is the Eddington limit. It sets a speed limit for accretion if the inflow is steady and the opacity is dominated by electron scattering. From that limit, and a typical efficiency of 10% for converting rest mass into radiation, one can sketch a timescale for mass to increase by a factor of e. The Salpeter time hovers around tens of millions of years. That seems generous until the clock of cosmic history is consulted. The most luminous engines appear when the universe is still young. To reach billions of solar masses in so little time requires growth at or near the limit, without long interruptions. The arithmetic is unforgiving. Nights of observation turn that arithmetic into a shout. Another rule comes from the coupling between radiation and matter. If the disk radiates more efficiently, the hole gains less of the falling mass. Thin disks around fast-spinning holes can throw away more energy as light before the gas crosses the inner boundary. That elegance brightens the source and slows the growth. Spin, therefore, cuts two ways. It keeps the engine luminous and drives spectacular jets when magnetic fields are present, but it taxes mass gain unless feeding is superlative. Observations of structured jets and compact hard X-ray continua imply rapid rotation in many cases. The paradox is simple. The brightest throats prefer high spin, and high spin prefers high radiative efficiency that fights growth. Yet mass measurements in the early universe insist on enormous totals. The rules are not wrong. They are incomplete for the conditions that mattered most. Feedback is the next guardrail. Energy and momentum released by the nucleus affect the fuel supply. Winds lift off the disk. Jets spear into the host and beyond. Shock fronts heat the interstellar medium and can sweep away dust and gas that would otherwise drift inward. In the common picture, feedback regulates feeding so that runaway growth is avoided and galaxies do not form too many stars. The largest black holes that shine in youthful epochs look as if they have evaded that regulation. Either the geometry is special and most of the released energy misses the inflow, or gas arrives in such dense streams that it does not care. The former option suggests narrow funnels or chaotic fueling that hides behind clumps and filaments. The latter imagines rivers from mergers or cold flows that are not easily deflected. Both modes ask theory to widen its riverbeds. The census of masses, against the calm motions of bulge stars, introduced a relation between the weight of the central object and the velocity dispersion of the surrounding stellar spheroid. That law implies a quiet negotiation between core and city. For the most extreme cases, the central mass looks overqualified for the hosting bulge, as if the negotiation went in one direction. The pact between nucleus and host is not broken outright, but it looks skewed. If the nucleus can jog ahead of the host early and pull the galaxy upward with it, the normal hierarchy of cause and effect softens. Growth may come in spurts where the engine leads and the stars follow reluctantly. Another cherished rule states that small things build large things. This is the spirit of hierarchical assembly. In dark matter simulations, halos merge and grow, and baryons settle into the centers that form stars and black holes. The largest black holes are therefore expected to be late harvests, the product of many mergers and steady feeding. Detections of immense masses very early test this patience. Either many seeds formed quickly in pockets that never respected small to large order, or the merger rate of black holes is higher and smoother than assumed, folding many seeds into one in a heartbeat of cosmic time. Both paths predict gravitational wave histories that are only now entering reach. While those histories are still being written in long-period ripples and higher frequency chirps, the visible mass at high redshift has already raised eyebrows. Gas that circles a hole does not simply fall, it must lose angular momentum. The rules of disks are clear. Viscous stresses, whether molecular, turbulent, or magnetic, move angular momentum outward and mass inward. The rate at which this happens limits how fast a black hole can eat, even before radiation pressure is considered. Numerical models of magnetrotational turbulence have filled in the microphysics, and global simulations have cultivated thick, hot disks that bend many of the early simplifications. The surprise from nature is that inflow at nearly critical rates can persist while still driving outflows and winds. The coexistence of hunger and rejection violates simple pictures where a single number controls everything. The rule transforms into a choreography where geometry, magnetic fields, and radiation decide moment by moment whether the inflow stays coherent. Other tensions arise from the chemistry of the young universe. Heavy elements make cooling more efficient, allowing clouds to collapse and fragment. The earliest epochs lacked those elements, which should have slowed the formation of very dense clumps. Yet intense activity around the largest black holes suggests that some regions reached the required densities rapidly. Perhaps shocks from structure formation or the influence of strong ultraviolet backgrounds changed the cooling pathways. If atomic hydrogen cooling held sway, then giant clouds could have collapsed into very massive objects without fragmenting into small stars. That line of thought relaxes the growth problem by inflating the birth weight of the seed. It also blurs the boundary between stellar and non-stellar origins, a revision that not long ago felt radical. The distribution of spins introduces another layer of shock. Mergers can both grow mass and either spin up or spin down, the result depending on the orientations at impact. Long periods of feeding from coherently rotating disks tend to align angular momentum and push rotation upward. Chaotic accretion from many brief episodes might randomize orientations and keep spins moderate. The most powerful jets argue for high spins and organized fields. If chaotic accretion is needed to keep efficiency low and growth fast, then the jet statistics demand a careful partition of fates. Some holes must live in tidy environments with aligned pipelines. Others must swallow from messy directions and yet somehow avoid catastrophic spin down. The rule that one feeding mode dominates gives way to a spectrum. Even the idea that nothing escapes is nudged by quantum reasoning. At the horizon level, pair creation and vacuum fluctuations conspire to create a faint leakage of energy. Over spans massively longer than stellar ages, that leakage would shrink the hole. The presence of any evaporation at all places a conceptual weight on the idea of permanence. The giants that tower over galaxies will not evaporate on any practical timeline. Yet the existence of a slow drip at all raises questions about entropy, information, and the bookkeeping of growth. The rule that a black hole is a one-way sink must share the stage with the rule that it has a temperature and a finite lifetime. That coexistence strains intuition and invites new frameworks where growth and fate are not simple opposites. Observations of stars on tight orbits around quiet central masses present another discipline. Motions trace clean ellipses and relativistic precession. Flares punctuate the light curve when small clouds encounter the inner environment. These scenes show that even in low power modes the same equations rule. Yet the disks sometimes vanish and return. Jets sometimes wake and then lapse into silence. The system toggles between high and low states, between radiatively efficient and inefficient modes. The rule that a black hole has a single lifestyle fails. Environment and supply chain matter intensely. Variability is not noise, it is identity. A final shock is emotional. Laws in physics usually comfort by reducing the unexpected to a template. The largest black holes transform that comfort into a challenge. They sit at the intersection of gravity, plasma physics, radiation, hydrodynamics, nuclear chemistry, and cosmic structure formation. Each field brings rules that fit the lab or the simulation. The cosmic engines take all those rules and superpose them in a regime where none of the usual approximations feel permanent. The result is not chaos. It is disciplined strangeness, like a cathedral built from blueprints that never anticipated such weight yet somehow hold. The guardrails still guide. The Eddington limit still speaks. Salpeter times still whisper a rhythm. Spin still taxes growth. Feedback still shapes weather on galactic scales. Disks still transport angular momentum by stresses that can be written and simulated. What changed is the realization that nature uses edge cases, narrow geometries, brief torrents of supply, and seed masses outside prior expectations. In those arrangements, the rules do not break. They flex. The shock is realizing how far they can bend without snapping, and how readily the night finds those bends when given enough gravity and time. Light arrives as messenger and accomplice. It tells tales of what gravity does to matter when the fall becomes irresistible. And it also carries the fingerprints of the last negotiations that matter holds with identity. A spectrum acts as a confession written in color. From the ultraviolet through the optical and into the infrared, a smooth rise and fall hints at a disk that is thin over great spans and hot enough near the center to glow like a nest of blue embers. The curve is not arbitrary. Temperature grades inward, each ring of gas shining with a thermal tone that overlaps its neighbors until the whole becomes a broad continuum. The slope of that continuum whispers about accretion rate and black hole mass, and the position of its peak announces how closely the inner edge of the disk hugs the last stable orbit. X-rays arrive with sharper intent. They bear witness to a compact corona of hot electrons that shrouds the inner disk. Seed photons from the surface scatter through that gas and harden, a process of Comptonization that turns soft light into a power law. Reflection sends a portion of the hard light back onto the disk, where iron atoms near 7 kilo electron volts answer with a line that is not a line in any gentle sense. Gravity and speed smear it into a broad red wing and a sharpened blue edge. The shape is a map of the space-time where it was born, a gravitational fingerprint whose asymmetry speaks to rapid rotation and deep potential. Modeling that profile reveals not only mass, but also spin, the property that encodes how much of the mass energy is stored as rotation and how tightly the last orbit approaches the brink. Variability is another language of light. It pulses and flickers on timescales from minutes to years. The shorter the timescale, the smaller the region that can coordinate it, a rule that turns light curves into rulers. Quasi-periodic oscillations sometimes appear as faint rhythms, a suggestion of orbital clocks or heartbeat instabilities in the innermost flow. Shot noise combines with correlated changes to produce power spectra that fall with frequency, a slope that traces turbulence and the cascade of fluctuations through the disk. When the continuum brightens, emission lines respond with a delay that measures the distance to the clouds that produce them. Reverberation mapping translates those delays into radii, and those radii into masses through the velocities encoded in the line widths. Light echoes offer cinema instead of still portrait. They watch the environment react in real time and give scale to what was otherwise only inference. Polarization rotates with meaning. The electric vector of light remembers the geometry of its birth. Synchrotron radiation from jets carries a polarization degree and angle that record the order of magnetic fields. Thermal light from the disk, scattered by electrons in an atmosphere that sits above the surface, gains a modest polarization aligned with the disk plane. General relativity twists the plane as photons curve around the hole. The rotation with energy and position on the sky promises a cartography of magnetic geometry and frame dragging, written not in brightness but in the orientation of the wave itself. Faraday rotation in radio combines with polarization to measure the density and magnetization of the plasma along the path, a probe of the sheath that cocoons the jet and the medium it pierces. Jets speak their own dialect of light. In radio and millimeter bands, synchrotron curves rise, flatten, and break, a signature of electrons accelerated to near light speed as they spiral along field lines. As those electrons slam into photons from the disk or from their own synchrotron C, inverse Compton scattering inflates a second hump in the spectral energy distribution, a mountain that climbs into X-rays and gamma rays. The ratio of the humps, their peaks, and the speed with which they shift betray the bulk Lorentz factor of the flow, the content of the radiating plasma, and the division of power between particles and fields. Knot motions across very long baseline images appear faster than light because angle and timing conspire to compress delays. The trick is pure geometry, yet it tallies honest speeds that approach the limit, a testament to engines that do not merely warm their surroundings but throw spears far beyond their homes. Dust rings surrounding the inner engine glow in the infrared when they absorb and re-radiate the ultraviolet light that rushes from the disk. The shape of that glow reveals the distribution of dust grains, their size, and their temperature. Changes in the central brightness ripple outward and warm new surfaces with delays that grow with distance, a slow breathing that converts central luminosity into a three-dimensional map of the torus. In some cases, the silhouette of the ring tightens into a narrow structure where polar dust forms a fountain. In others, the geometry resembles a clumpy wreath that feeds shadows back onto the disk and modulates the multi-wavelength output like a slow shutter. Gravitational lensing of distant active nuclei adds layers to the script. When a galaxy lies along the line of sight, it divides the quasar into multiple images. Each image arrives with a different time delay. Brightness fluctuations in the source appear in sequenced replay, letting observers measure both the scale of the central region and the matter distribution in the lens. Microlenses within the lensing galaxy, small stars and remnants, magnify patches of the disk with preference for shorter wavelengths where the disk is smaller. Chromatic microlensing measures the size of the emitting zones across the spectrum and tests the classic prediction that radius scales with wavelength to the 4/3 power. Deviations from that scaling ask for more complex disks, winds, or coronal geometry. Closer targets yield silhouettes rather than reports. At millimeter wavelengths, interstellar scattering thins and interferometers that span the Earth stitch signals into a single eye with a resolution measured in tens of micro-arcseconds. The ring that frames the darkest interior records the place where photon orbits skim the edge before surrender. Bright crescents arise where the flow rushes toward the observer, adding Doppler weight to those pixels. The diameter of the shadow depends primarily on mass, and the brightness asymmetry depends on spin and viewing angle. Small departures from circularity hint at charge-free yet vigorous magnetic pressure. The image is not a simple photograph. It is a reconstruction from sparse data, but within it the grammar of general relativity becomes visible art. The photon ring promises higher-order images if resolution sharpens, each nested echo a contour of light that glanced again and again at the brink. Time-dependent spectra reveal winds. Broad absorption troughs bite into the ultraviolet, blue shifted by tens of thousands of kilometers per second. Those troughs wax and wane, suggesting clumps that slide across the beam and change the covering of the source. X-ray spectra carry edges and lines that trace outflows as well, with velocities that range from gentle breezes to ultra-fast gusts that approach a fraction of light speed. These winds steal a portion of the accretion power and return it to the galaxy. They also modify the inner radiation field, shading parts of the disk and hardening the continuum that reaches the corona. Light, in this role, is both tracer and participant. It cools, it heats, it drives, it reveals, all at once. Tidal disruption events contribute sharp flares to an otherwise steady diet. A passing star wanders within the tidal radius and is pulled into filaments that loop into an ellipse of gas. The fallback rate rises with a t to the negative 5/3 law, a cold mathematical promise that becomes a hot blue transient in practice. Emission lines bloom in oxygen, nitrogen, and hydrogen as debris slams into itself and circularizes. Soft X-rays roll upward as the new disk forms. Late-time spectra acquire helium and metal lines sculpted by winds. The sequence reads like a short novel, about a new disk being born in fast motion, and from that text, the mass of the central black hole can be read. Even silence has content. Low luminosity nuclei shed most of their power as outflows rather than light, and their spectra flatten into hard, inefficient states. The lack of a big blue bump, the hallmark of a bright disk, tells of a flow that has become thick, hot, and optically thin. Radio jets in those systems can dominate the output. The partition between radiatively efficient and inefficient modes, written in spectral shape, suggests thresholds in accretion rate and transitions in disk structure. Light, by its absence in one band and presence in another, marks which architecture is at work. Together, these signals form a dossier rather than a single portrait. Continuum slopes, trace temperatures and radii. Emission line profiles and their lags provide a ruler and a scale. Reflection features whisper about the curvature of space-time and the spin of the engine. Polarization sketches magnetic fields and measures geometry. Variability compacts the theater and times the acting. Jets translate rotation and field into travel and make distance itself luminous. Shadows, when they can be resolved, test the very shape of space where gravity is absolute. Each channel extends understanding, and each channel opens a fresh angle of unease. The light is not comfort. It is a brilliant outline wrapped around a region that refuses to speak directly. The glow is all prelude and aftermath. The center remains the stillness that bends every wavelength into a halo of revelations that orbit a secret. Hunger gathers in patterns that look like weather written on gravity. When gas approaches the brink with more enthusiasm than rules predict, the flow thickens and the light that should blow it back becomes trapped within. Photons try to flee outward, but are dragged inward by matter that moves almost as quickly. A swollen structure forms where pressure and motion negotiate in a hot compromise. A disk that is not thin but not a sphere, a funnel with bright walls. The brilliance still pours out sideways and upward, yet the flood toward the center goes on. Limits that once looked firm soften when the engine can grow while its own radiance is held captive. Appetite and confinement reinforce one another until the geometry itself looks like a storm eye. Magnetic fields add a harsher grammar. As inflow brings flux with it, lines pile onto the horizon and grip the plasma with a ferocity that rivals gravity. Accretion can stall at the gate when the pressure of those fields resists any further delivery of material. The engine enters a state where power rises because the magnetic grip extracts rotational energy, flinging it into jets that punch outward with stubborn coherence. The feast pauses at the table edge while energy explodes into the night. Then something yields and the gate opens again, the inflow surges, and the cycle resumes. The scene alternates between choking and gorging. In the alternation, the hunger looks intelligent. It is only the logic of fields and motion coupled so tightly that they imitate intention. Disks do not always behave as if they were single pages. Tilt can break them into rings that precess at their own rates. Warps develop and sometimes tear, allowing inner regions to slip relative to outer ones. Each tier sharpens inflow into brief downpours that heat the inner atmosphere and summon flares across the spectrum. The central object, spinning fast, tries to align the inner rings with its equator, while outer regions still remember a different direction. The result looks like a nest of shining saw blades, each with a phase and a pulse. In such configurations, variability ceases to be a nuisance and becomes the main story. Timescales that once suggested modest radii now speak of structures that topple and rebuild within hours. The appetite grows not only in rate, but in complexity, as if the mouth had acquired many tongues. Obscuration hides some of the drama and makes it more disturbing. In many cores, the central zone is swaddled by dust and gas, thick enough to blunt even hard X-rays. Light that tries to tell what is inside reaches the observer only after scattering along crooked paths or reflecting off metal-rich clouds. Flux rises and falls as if a hand had closed around the throat of a lantern. In some nuclei, the costume changes outright. Broad lines vanish, the ultraviolet continuum dims, and the object appears to become a different class, only to return months later. The name for such behavior is polite, changing look. The experience for the observer is a deepening of unease. Identity itself becomes a function of the supply chain, the dust factory, and the arrangement of clouds that stroll across the beam. Jets stiffen the spine of hunger with their own victories. When rotation and field align in the right geometry, a column of magnetized plasma leaves the inner region at speeds that reduce time. Knots move along the beam like beads flicked along a string. Shocks ripple, and the spectrum scrolls through colors as electrons are accelerated and then cool. The beam drills through the interstellar medium, finds the halo of the host, and keeps going until it presses on the diluted gas between galaxies. Wherever it meets resistance, it deposits momentum and heat, carving cavities and pushing back the very supply that might one day return inward. Hunger here engineers its own drought and compensates by lengthening the straw. A galaxy can look quieter in starlight even while its nucleus pumps energy into space with near-perfect aim. Sometimes the fuel arrives in storms that defeat the usual regulation. Filaments of cold gas slip down the potential well-like rain sliding on glass. They fragment but retain coherence long enough to reach small radii, where they are promptly shredded into a luminous spray. These arrivals are not gentle flows but avalanches, and the engine responds with episodes of brightness that match the violence of delivery. Winds lift off the disk at the same time, but the incoming rivers carry more weight than the outward breath can repel. Hunger deepens by momentum rather than by persuasion. The nucleus lights the city and erodes it in the same season. Binaries in the core escalate the drama. When galaxies share tidal scars and their centers draw near, two massive objects orbit within a common envelope of stars and gas. Torques transfer angular momentum to the environment and shrink the dance. On scales still far larger than any horizon, the pair shakes its cage and stirs inflow from new directions. Disks form around each member, and a larger disk wraps the pair, a hierarchy of wheels with misaligned planes and nested cavities. Gas streams slap into the mini-disks twice per orbit and feed them in bursts, producing periodic flares that translate dynamics into light. As the separation drops, gravitational waves begin to drain energy in a whisper that grows into a roar. Even before merger, the hunger increases because two throats call to the same pantry. After coalescence, recoil can kick the remnant into a long, slow arc through the host, as the anisotropic emission of space-time waves gives the object a shove. If the inner disk stays bound, it becomes an off-center furnace, feeding in exile, while the core it once occupied tries to remember how to be quiet. Trails of blue stars sometimes follow where jets had once carved channels. The galaxy wears bruises that memory cannot explain without the language of mergers and recoil. Appetite leaves footprints even when it tries to leave no trace. Coronal physics raises the temperature of uncertainty. Electrons in the tenuous region above the disk heat until pair production threatens to swamp the volume with electron-positron fog. The temperature then stalls at a thermostat set by annihilation and cooling. Yet observations of rapid hard X-ray changes demand compact sources that flirt with those limits. Tiny regions rise and fall like sparks caught in wind, and the spectral slope pivots as if someone were adjusting the heater. The smallest structures, perhaps magnetic islands born from reconnection, flare in patterns that hint at a granular hunger, a feeding that happens in packets rather than in a smooth pour. Evidence for extreme outflows adds another notch to the escalation. Absorption lines shift by velocities that lick the edge of a tenth of light speed. P Cygni profiles and blue wings on iron features betray winds with deep roots in the gravitational well. These winds do more than carry energy outward. They steal angular momentum from the inner regions and let matter drop further in. The same breath that clears the surroundings greases the fall. The paradox is elegant. A gale that would seem to starve the core also sharpens its teeth. Particles leave with ambitions of their own. Shocks in jets and the shear at their boundaries provide factories for cosmic rays that travel far beyond any one galaxy. High-energy neutrinos occasionally arrive from directions that align with active nuclei, messengers that touch almost nothing along the way and therefore accuse their birthplace with quiet certainty. The hunger that extracts energy from rotation and infall does not finish its work by lighting gas alone. It writes its appetite into the cosmic ray background, and into ghostly particles that whisper of collisions at energies no terrestrial machine can match. The population statistics raise the stakes with every new survey. Obscured engines are counted with infrared eyes that glow with reprocessed light. Hard X-rays fill in the deficits. Radio maps expose cores that otherwise look like sleepy bulges. As the inventory grows, the fraction of hidden growth stages rises. The picture tilts toward a universe where the loud phases are only the tip of a practice conducted mostly behind curtains. If most mass arrives during shrouded episodes, then the engines live much of their lives inside their own cocoons. Hunger, in that case, is not a spectacle, but a habit. Spin measurements accumulate and argue among themselves. Reflection in some spectra suggests rapid rotation near the maximum allowed by general relativity. Thermal continuum fittings in certain stellar mass objects also prefer high values. Yet in other systems, the evidence points to moderate spins. The diversity complicates any single story. If rapid rotation is needed for the most impressive jets, yet slows mass growth by increasing efficiency, then the catalogue requires a distribution of fates in which some engines pay the cost and become lighthouses, while others choose dimmer lives that fatten the horizon. Appetite diversifies not only in rate but in strategy. Amid all this, the central fact remains that gravity has no saturation point. It deepens without complaint as mass arrives. What changes with escalation is the way the environment answers. The surrounding medium bucks and flares. The magnetic cage tightens and snaps. The disk pretends to be solid, then becomes foam. The core drinks and chokes, then drinks again. Observers at every wavelength catch scenes that refuse a single map. Hunger, measured by light and wind, reveals a face with many eyes. Each eye opens into a new room, and each room holds a different version of the same simple craving for more curvature, more fall, more power wrung from the difference between up and down in a universe that invented height just so things could descend. Origins matter because beginnings set the pace for everything that follows. The largest black holes command respect, partly because their childhoods appear compressed into the briefest dawns of cosmic time. 3 families of birth stories compete for that first cradle. One begins with the deaths of the first stars. Another imagines clouds that never fragment into starlight at all. A third peers even deeper and suggests that some seeds were written into the fabric during the fire of creation itself. The first stars lit the universe without metals to guide their cooling. Hydrogen and helium alone allow only limited paths for heat to escape, so the clouds that formed those pioneers likely collapsed into heavier cores before fragmentation could take over. The result would be massive stars with short tempers and shorter lives. When such giants reach the ends of their nuclear paths, some would find no pressure sufficient to halt collapse. Their hearts would compress into black holes with masses tens or hundreds of times that of the Sunday. If such remnants found gas quickly and consistently, they could begin to climb the ladder towards supermassive scales. Yet arithmetic remains stern. To reach 1 billion solar masses that way requires feeding near the radiative limit for many cycles, or episodes where the flow bypasses that limit altogether. A second path suppresses starlight entirely and accelerates the descent. In certain halos of dark matter with masses large enough to hold gas at 10,000 Kelvin, atomic hydrogen cooling can carry away heat without the assistance of molecules. If near neighbors flood the region with ultraviolet radiation in the Lyman-Werner band, molecular hydrogen is destroyed and fragmentation is arrested. Without fragmentation, the cloud falls inward as a whole rather than breaking into a cluster of small stars. The center can then build a supermassive star or a quasi-star, where a nascent black hole forms inside an extended envelope that regulates the inflow like a thermostat. The envelope radiates at a brightness that hovers near the classical limit, while the core swallows at rates that make time irrelevant. When the envelope finally dissipates, a direct collapse black hole remains, already carrying 100,000 or even 1 million solar masses. The ladder shortens dramatically when the first rung is so high. Gas dynamics help. Streams within forming galaxies flow along filaments of the cosmic web. When 2 or more of these highways converge, they can deliver mass toward the center faster than turbulence can reroute it. Angular momentum, the great obstacle to collapse, can be bled away by bars within bars, where large-scale non-circular motions create smaller structures that continue the drain at each step. The Toumri stability parameter tracks when a disk can hold its shape and when it begins to fragment. Under strong inflow and heating, Q can hover near unity, keeping the disk marginally stable while still allowing transport of mass. In that marginal state, gas moves inward as if sliding down a greased ramp, sustaining a birth channel for direct collapse seeds. Dense star clusters offer a third astrophysical cradle. In environments where the initial density is extreme, massive stars can suffer repeated collisions before they evolve off the main sequence. Runaway mergers build a single very massive star that lives briefly and collapses under its own gravity. The remnant emerges heavier than any normal core collapse product. With sufficient supply, dynamical friction draws additional compact objects inward, and mergers add steps to the mass ladder. The pathway is not smooth, but the steps are steep. A more radical idea steps outside astrophysical assembly altogether. Primordial black holes would be relics of the earliest instance after the Big Bang, formed from rare overdensities in the primordial plasma, or from phase transitions that briefly changed the equation of state of the universe. Most such primordial objects, if they were very small, would have evaporated through quantum leakage long ago. Yet in narrow mass windows, constraints allow a population that could have survived and perhaps contributed seeds that later grew where gas was available. Microlensing, cosmic microwave background distortions, and dynamical signatures limit this family severely, but the concept remains a pressure point at the interface between cosmology and astrophysics. Even a small population would alter the head start for central engines. Growth after birth depends not only on supply, but also on the geometry of the infant's nursery. Early galaxies were compact and clumpy. The gravitational potential wells were shallow compared to present giants, yet inflow along filaments was vigorous. Cold streams could punch through shock-heated halos and arrive at the center without warming. The density, coupled with low metallicity, reduced radiative cooling at small radii and favored thick disks that fed the center while choking on their own light. Super Eddington episodes then become plausible, not as a daily habit, but as a series of bursts that lift a seed dramatically before feedback has time to rearrange the stage. In such convective, photon-trapped flows, radiation is carried inward with the gas and released closer to the horizon, weakening its ability to throttle the inflow. Efficiency becomes a sliding quantity, and the calendar suddenly grows generous. Spin enters at birth and never leaves. Seeds born from collapsing stars inherit rotation from their progenitors. Direct collapse flows naturally impart angular momentum to the forming core. Mergers tilt and twist the sum. High spin raises radiative efficiency and can support jet launching through magnetic extraction of rotational energy. Low spin reduces radiative losses and accelerates mass gain. A seed that experiences many brief episodes of feeding from changing directions may keep a modest spin through cancellations. Another that draws from a long-lived, coherently rotating disk will spin up and pay the cost in slower growth, but gain in power per unit mass. The population of seeds likely carried a spectrum of spins that set destinies long before the first quasar blazed. Radiation from neighboring newborn stars and black holes sculpts the nursery. The same ultraviolet field that suppresses molecules in one halo might be absent in another, allowing fragmentation and slowing collapse. X-rays from a growing seed can preheat gas and raise the gene's mass, changing how clouds break apart and perhaps assisting later inflow by smoothing small-scale structure. The interplay between feedback and feeding at these earliest times is delicate. A single burst from a new core can clear its surroundings and enforce a pause. If fresh streams then arrive along a different direction, the engine may restart with a new angular momentum vector. The resulting misalignments prime disks to warp and tear later, setting a chaotic tone from the beginning. Kicks from asymmetrical emission during mergers threaten to eject young black holes from shallow potentials. A seed that merges with a companion shortly after formation can receive a recoil that launches it far from the center or even out of the nascent galaxy. Retention depends on mass ratio, spin magnitudes, and spin orientations. If the pair merges within a deepening well, the remnant can return on an elongated orbit, stirring the central region and collecting new fuel each time it passes. If the well is too shallow, the core escapes and the clock resets until new seeds form. This roulette adds noise to the history of any one galaxy and spreads seeds into the halos where they might later be recaptured. Chemical enrichment changes the map quickly. The first supernovae sow heavy elements that open new cooling channels. Once metals exist, dust forms and clouds can shed heat efficiently. Fragmentation blooms, and the next generation of stars tilts the mass function toward lower values. Direct collapse requires pockets that remain metal poor and are bathed in strong dissociating radiation. The universe does not provide those pockets uniformly. Their rarity means that the direct collapse channel may be exceptional but consequential. A few massive seeds placed well can dominate the bright records of the next few 100 million years. Observational footprints of these births are subtle but not invisible. A direct collapse event should shine briefly as a luminous yet cool transient, heavy in the ultraviolet and soft X-rays, before the envelope is stripped. A cluster runaway might leave behind a compact starburst surrounding a nascent black hole and a chemically unusual signature in the surrounding gas. Primordial relics would have few immediate telltales beyond their demographics, but their presence would echo in the statistics of early quasars and in the distribution of black hole masses within dwarf galaxies. Each channel writes a different preface for the same epic. The deepest uncertainty remains the balance between time and supply. If the seeds begin at tens of solar masses, the calendar demands persistent feeding and likely supercritical episodes. If the seeds begin at 100,000 solar masses, the calendar relaxes and asks instead for rare conditions to have existed at just the right sites. Reality may refuse to choose. The sky can accommodate multiple beginnings, with each galaxy sampling the options that its web position, neighbors, and history afford. A mosaic of childhoods can still converge on similar adulthoods if the later environment imposes shared constraints. In the end, the terror of the largest black holes is not only their final depths, but the speed with which they learn to be deep. The Dawn universe, thin and new, already hosts engines that behave like veterans. Beginnings in that era could not have been gentle. Gas must have fallen in sheets. Stars must have died young and heavy. Clouds must have chosen collapse over light. Or gravity itself must have whispered seeds into being when everything was still hot enough to remember the first fraction of a second. Whatever the recipe, the ovens were hot and the loaves rose quickly. The rest of cosmic history would have to adapt. Gravity prefers company. Galaxies do not drift alone forever. Their orbits around shared mass bring them into embrace, and when they meet, the central engines respond like furnaces fed with dry timber. Torques awaken in the tangled stars and gas. Angular momentum flows outward along spiral arms and bars that bloom inside bars, each structure a lever that pries the inner gas loose from its circular comfort. The result is a migration toward the heart. Clouds fall inward and collide. They lose memory of their previous paths and settle into a compressed disk that shines with newborn stars and shudders with shocks. In the middle of this storm, a black hole waits with patient appetite, and patience is rewarded. Two nuclei deepen the effect. As the galactic centers draw near, each heavy object drags a wake of stars that saps orbital energy. This slow handshake, written by dynamical friction, shrinks the distance between them until they become a binary encircled by a common reservoir of gas. The gas does not sit idly by. It forms a circumbinary disk that streams inward through tidal channels, feeding miniature disks around each black hole. Every half-orbit, the streams slap the mini-disks and flare, converting gravitational energy into light with a cadence that tracks the dance. The inward march accelerates as torques and tides pass angular momentum from the pair to the gas, and the binary hardens in a steady beat toward the final approach. Runaway feeding thrives in this geometry. Instead of a gentle drizzle of fuel from a quiet galaxy, a merger brings torrents. Colliding flows compress to high densities that cooling can handle only with difficulty. Shocks heat the gas but also create pressure gradients that drive more mass inward. The accretion rate can leap beyond the brightness limit that radiation alone would impose in a thin disk. Thick, photon-trapped flows emerge, and the central engines fatten in spurts. The same fireworks that birth a starburst also build the core. In diagrams, this looks like a closed cycle. In the sky, it looks like a city set on fire at the center while the outskirts watch. Supermassive growth is not the only outcome. Spin is rewritten during mergers. If two holes approach with misaligned angular momenta, the final orientation reflects a vector sum that remembers the past only through a few numbers. A black hole that was once moderate can become rapid. A black hole that was once rapid can be slowed. The product inherits a new potential for jet launching and a new efficiency for turning infall into light. In effect, a merger does not simply add mass, it reshuffles the deck of future possibilities. That reshuffling feeds forward. A rapidly spinning remnant launches stronger jets that excavate cavities and heat halos, changing how the next round of gas arrives. A modestly spinning remnant loses less energy as radiation from the inner disk, so the same fuel builds more mass. The sequence of meetings writes the eventual personality. Stars are not passive during these episodes. Their orbits are torqued by the evolving potential, and many are thrown onto plunging paths that graze the feeding zone. Some are shredded and digested in brief, furious meals. Others slingshot outward with new speeds, escorting energy away and helping the binary tighten further. In triaxial or barred potentials, fresh stars wander into the vicinity of the pair more efficiently than in a symmetric core, solving the bottleneck that once seemed to stall binaries at parsec scales. The environment feeds the loss cone with a steady supply of victims and messengers, and the shrinking continues. Not all collisions are generous with gas. Dry mergers between galaxies poor in interstellar medium deliver mass with little new fuel. Even then, the core grows because two horizons unite. A dry event can also create a boxy remnant with orbits that refill the center with stars on long timescales, maintaining the supply of interactions that bring additional compact objects inward. Later, when the galaxy breathes in a new stream from the cosmic web or swallows a smaller, wetter neighbor, the infrastructure for runaway feeding is already in place. Triples complicate the journey in ways that favor closeness. If a third black hole arrives before the first pair completes its union, resonances and chaotic exchanges can pump eccentricity and shorten the time to contact. An eccentric binary couples to the surrounding gas differently. Pericenter passages are briefer and more violent. Heating spikes and streams crash with added force into the mini-disks. Periodic signatures in light curves become sharper and less sinusoidal, as if the engine were coughing on a schedule. The language of variability begins to speak celestial mechanics with an accent that touches plasma physics. Evidence for dual engines appears in narrow double peaks within some emission lines, hinting at two broad line regions moving with distinct velocities. In radio, pairs of compact cores light up within a single distorted host. In X-rays, separated hard sources flicker in offsets that betray two throats working in parallel. Sometimes the fingerprints are indirect, like wiggling jets whose precession implies a binary torque, or periodic optical modulations that suggest a clock longer than any single orbit near the horizon. Whatever the channel, the theme is consistent. When galaxies collide, the center learns to eat with both hands. Recoil writes a different kind of signature. After the horizons merge, asymmetric radiation of gravitational waves can kick the remnant. If the impulse is strong enough, the black hole departs from the nucleus carrying with it the inner disk. As it travels through the host, it shines as an off-center beacon with a spectrum flavored by high velocity relative to surrounding gas. The disturbance in the core remains behind as swirling stars and shells, a fossil that points to the event even after the light has faded. In less extreme cases, the remnant oscillates through the central potential well, stirring gas and triggering repeated, lopsided inflows that extend the feeding epoch. Runaway feeding leaves imprints on large scales. Jets inflated during the feast carry momentum that sculpts interstellar and intracluster gas. Cavities bloom like bubbles in X-ray images of hot atmospheres. The edges of those bubbles curl where sound waves and weak shocks ripple outward. These ripples are not mere decorations, they are the receipt that shows energy delivered beyond the nucleus into the broader environment. That delivery throttles future cooling and star formation, making the next episode of feeding both less likely and more dramatic when it finally arrives. The cycle resembles breathing with long inhales and punctuated exhalations, and mergers expand the lungs. Inside the funnel, magnetic fields tighten the knot. As inflow grows, so does the magnetic flux delivered to the horizon. A magnetically arrested state can arise, where pressure from wrapped field lines holds the gas at the doorstep. The engine then taps rotational energy and drives jets that can dominate power output. In merger-fed systems, the flux supply is generous, and the arrested condition can persist longer. That persistence bridges episodes of high accretion and episodes where geometry alone keeps the engine bright, turning a burst of feeding into a season of influence. Disks can also become eccentric under the gravity of a binary. The inner rim of the circumbinary disk precesses slowly, and streams alternate in strength as the pattern slips. This modulation resonates with the pair, and alters the rate at which angular momentum is removed. In some configurations, the binary can even reverse the normal torque sign and migrate outward temporarily, like a skater pushed back by a passing partner. When the sign flips again, the inward race resumes with renewed vigor. The feeding history in such a system is a palimpsest of superposed cycles, some written by hydrodynamics and some by geometry. The most unsettling aspect is speed. Pathways that looked gradual can, in these arrangements, become torrents. A black hole that would otherwise need many calm ages to double can do so in a handful of events. Each merger resets the stage and invites a new flood. Each flood lifts mass and shifts spin. Each shift alters how the next flood will couple. The compounding creates a staircase that climbs steeply even within the youth of the universe. The impression for an observer is of engines that reach adulthood with indecent haste and then continue adding decades in bursts whenever fate brings them a partner. Runaway feeding and mergers, therefore, compose a single grammar. Torques drain spin from orbits and give it to gas. Gas returns the favor by marching mass inward. Binaries harden on wakes, then on tides, then on space-time itself. Recoils bruise the host and light transient beacons. Jets write the minutes of each meeting onto the airy halls that galaxies share. The result is a record of appetites that alarm not because they are chaotic, but because they are efficient. Gravity shows again that it needs only a few rules and a crowded room to turn opportunity into inevitability. Rotation changes gravity into choreography. A mass that spins drags the surrounding space-time with it, twisting the grid of cause and effect so that anything nearby is compelled to turn. The effect is not persuasion but geometry. Frames of reference that would otherwise sit still are forced to rotate. Gyroscopes precess, as if honoring an invisible hand. The swirl deepens toward the center until a boundary appears where standing still becomes impossible. That boundary is the surface of the ergosphere, a sleek, oblate sheath around the horizon where every path must co-rotate. Inside that sheath, time and space trade roles in a way that permits a remarkable accounting trick. Orbits can carry negative energy relative to infinity. The mathematics allows an intruder to leave with more energy than it brought, the difference paid by the whole in a slow tax on its spin. The most austere version of this exchange is a thought experiment that imagines a particle splitting inside the ergosphere. One fragment falls inward on a negative energy track. The other escapes with a surplus, and the black hole spins a little slower than before. This is the Penrose process. On a chalkboard, it is elegant. In nature, it needs a clerk to arrange the split and control the trajectories with precision that gases and fields rarely possess. Magnetism provides the clerk. When field lines thread the rotating throat, they are wound into a helix and twisted until tension launches waves and currents that stream outward. The flow carries electromagnetic energy away as a pointing flux. a rotating magnetosphere extracts the angular momentum of the hole and deposits it in a pair of narrow, oppositely directed beams. The jet engine that results operates without turbines or nozzles. It is a conduit between rotation and vacuum, a generator that uses the black hole as the rotor and the magnetic flux as the stator. The power scales with the square of both the magnetic flux and the spin parameter. Even modest increases in either can produce dramatic rises in luminosity. In simulations where inflowing gas delivers more flux than the hole can swallow, a magnetically arrested state forms. Dense ropes of field pile at the horizon and resist further inflow, while the rotation of the hole forces the bundle to launch a jet that is more electromagnetic than material at its base. The engine becomes a lighthouse powered as much by spin as by falling matter. Spin does not only feed beams, it also sharpens the inner edge of the accretion disk. The innermost stable circular orbit draws closer to the horizon as rotation increases in the same direction as the disk. For a non-spinning black hole, the last stable orbit sits at 6 gravitational radii. With rapid rotation, it can creep to little more than 1 gravitational radius. The closer the edge lies, the deeper the gravitational well that the gas must climb if it were to escape. The difference in energy between a distant circular orbit and the last stable one dictates how efficiently mass can be converted into light. For no spin, a thin, radiatively efficient disk converts roughly 6% of rest mass into radiation. With near maximal spin in the same sense as the disk, that efficiency can triple. A theoretical extreme would allow even more, but capture of returning photons by the hole enforces a practical ceiling. Rotation therefore brightens the engine per unit mass and changes the color of the light by shifting more of the glow to hotter inner rings. Where the disk meets the magnetosphere, the physics of plasmas shivers with detail. The rotating field creates a light cylinder at which co-rotation would demand the speed of light. Inside that cylinder, currents flow and charge densities adjust to keep electric fields from accelerating particles indefinitely, yet gaps can form where the plasma supply is thin. In those gaps, electric fields parallel to the magnetic field ignite pair creation, releasing avalanches of electrons and positrons that short out the field and then thin again. The process repeats in a flicker that seeds the jet with fresh plasma. The jet accelerates gradually as magnetic energy converts to bulk motion, crossing surfaces where the flow outruns Alfvén waves and then fast magnetosonic waves, trading rigidity for speed while remaining collimated by the very field that launched it. Observationally, rotation leaves a pattern of signatures. Iron fluorescence from the inner disk is sculpted into a skewed profile by both gravity and Doppler motion. The depth of the red wing and the sharpness of the blue horn encode how near the last stable orbit approaches the brink, and therefore speak to spin. The continuum from a hot disk around a stellar mass black hole in a quiet galaxy bends in a way that can be fit with models whose inner radius depends on spin. Polarization angles rotate with energy as photons thread their way through the curved geometry close to the hole, promising a clean test of frame, dragging when measurements become sharp enough. On horizon scales, silhouettes reveal bright crescents weighted by the side that approaches the observer, an asymmetry enhanced when rotation aligns with the viewer. The diameter of the shadow depends mostly on mass, yet the glow around it reads spin and viewing angle like script around a seal. Jet power correlates with these rotational clues in a manner that suggests a common cause. Systems that display broad, skewed reflection features consistent with high spin often wield beams that inflate cavities and light radio lobes far from the nucleus. Polarization in those lobes records ordered magnetic fields aligned with the axis of the jet, a memory of the helical structure wound near the engine. Variability in high-energy bands arrives in fast, sharp bursts from compact regions that ride shocks along the beam. Superluminal motions map apparent speeds that imply bulk Lorentz factors of 10 or more. The entire apparatus performs as if a spinning core, a tight field, and a thickened disk were co-conspirators. Spin can also misalign the dishware. If the inflowing gas arrives with an angular momentum vector not aligned with the black hole, the inner disk feels a torque that makes it precess. Viscosity and warping communicate that precession outward, and a compromise emerges in which the innermost rings align with the equator of the whole, while the outer disk keeps its original tilt. The transitional region can tear into separate planes that exchange mass in abrupt streams. Precession imprints slow changes on jet direction, bending its path into gentle helices and tilting the beam so that its brightness sways with the angle to the line of sight. This dance is a visible register of the Lentz-Thirring effect at scales far beyond any laboratory. Rotation is not eternal. The same processes that exploit it erode it. A jet that carries away angular momentum spins the whole down over long seasons. Mergers deposit new angular momentum that may speed it up or slow it depending on orientation and mass ratio. Prolonged feeding from a coherently rotating disk spins it up. Feeding in many short, misaligned bursts can keep the rotation moderate by averaging directions. As a result, the universe holds a spectrum of spins rather than a universal value. The distribution encodes the balance between meals measured in millions of years and meetings measured in orbits of galaxies. The ergosphere itself is an arena of curiosities. Inside it, no observer can keep a fixed compass relative to far stars. Light cones lean until all permissible motions require a whirl. Energy extraction there does not violate local conservation laws. It exploits the bookkeeping of what energy means when time translation symmetries are twisted by rotation. Negative energy orbits do not imply negative mass things. They imply that the definition of energy available to distant observers can be written in ways that permit deposits into the balance sheet of the whole. When magnetic fields guide plasma onto such orbits, the accounting becomes practical and the jet becomes a receipt. At larger radii, the jet behaves like a living structure. It entrains a sheath of slower plasma around a spine that carries most of the electromagnetic power. Instabilities wrinkle the interface between spine and sheath, braiding the flow into knots and filaments that radiate with polarized synchrotron light. Shocks form where the external medium pushes back, or where faster shells overtake slower ones. Electrons gain energy in these shocks, and in regions of magnetic reconnection, then cool by synchrotron and inverse Compton processes. The spectrum keeps two humps, one from gyrating charges and one from photons boosted to high energy by those same charges. The ratio and location of the peaks drift as the engine and environment change. A weather report written in frequency rather than cloud. Spin threads all of this with a single instruction. A faster whirl draws the inner edge inward, brightens the disk per gram of fuel, and strengthens the ability of fields to tap rotational energy. A slower whirl fattens the black hole more easily at the cost of a gentler light. Between these poles lies a landscape of outcomes where jet strength, spectral character, and variability patterns blend. The terror here is not violence for its own sake. It is the realization that the geometry of space-time can be twisted into a tool that harvests pure rotation and turns it into ordered energy that crosses interstellar and intergalactic miles with narrow purpose. A silent axle spins in the dark, and the universe builds engines around it that do not tire. Gravity practices surgery without instruments. It reaches into a body with nothing but curvature and pulls it apart along lines that follow no visible incision. When a star wanders too near a black hole, every layer of that star learns a different lesson about distance. The side that faces the abyss falls harder. The far side lags behind. Tension grows. The star elongates until its roundness fails, and its shape narrows into a ribbon whose atoms feel both flight and fall at once. Tides right this change. They are not waves on a surface but stresses born of gradients, a mathematics of difference that becomes fate. There is a boundary around every massive object where cohesion yields to the pull of gravity outside. For planets orbiting planets, that line is called the Roche limit. For stars flirting with black holes, the boundary is a curve in phase space rather than a neat shell. But the idea is similar. Cross close enough, and no internal pressure can keep the body whole. The star does not explode. It unspools. Its center of mass follows a tight path while its limbs trail behind, then overtake, then loop, until a single stream wraps the black hole like silk thrown into a storm. The violence is timed by orbital speed. At closest approach, the ribbon thins and the density spikes. Compression across the short axis can become fierce enough to trigger shocks that race from face to face. In some passes, the entire star perishes in a single visit. In others, only an outer layer is shaved off, and the core survives to return on an elongated orbit. These partial disruptions leave scars. The survivor swells, dims in photos, and later shrinks again, carrying missing mass and a memory of heat deposited by tidal work. Repetition is possible. A near miss can become a periodic levy on the star's envelope until the orbit changes or the core finally yields. The mass of the black hole sets a ceiling on spectacle. If the hole is too heavy, it swallows a solar-type star whole without letting the debris radiate outside the horizon. There is a sweet interval where the event horizon is smaller than the star's disruption radius, so the tearing occurs in view of the universe. That interval ends around several 100 million solar masses for main sequence stars. Below that scale, flares can bloom. Above it, the act becomes private, and light tells no tale. Giant stars, with their puffed envelopes, bend that boundary in the other direction and can be unmade by heavier holes. The mapping between victim and executioner is written in density profiles and size as much as in mass. The first bright signal arrives when torn matter begins to fall back. Parts of the ribbon have slightly different binding energies. The most bound section turns first and returns after a characteristic time that depends on the black hole and the size of the star. After that, a rain of debris arrives with a rate that falls away like a power law. Observers reduce the blossom of light to a curve and find the signature decline, a brightness that fades roughly as time to the -5/3. Reality embellishes the template. Circularization is not instantaneous. General relativistic precession tips the returning stream, so it collides with itself on the far side of the black hole. Shocks there dissipate orbital energy and help the stream collapse into a short-lived disk. Each collision wastes order and sets heat free. The result is a flare that begins blue and soft and sometimes grows a hard tail as the newborn disk thickens and a coronal skin kindles above it. Spectra carry the fingerprints of chemistry and kinematics. Hydrogen lines rise and broaden, then thin. Helium lines join or even dominate when the stripped layers came from a star that had already peeled away its hydrogen, or when wind and geometry obscure the cooler gas. Metal lines appear as the photosphere recedes, and deeper layers show their composition. Blue winds with thousands of kilometers per second in their shift bite into the continuum as absorption troughs. On their edges, fine structure and resonance lines ladder upward. Speaking of ionization, states that roll with changing luminosity. At later times, infrared echoes from dust that has been heated by the flare glow in gentle arcs of their own, mapping the geometry of the surrounding medium in light delayed by distance. Sometimes a jet erupts during the meal. If the magnetic flux at the horizon is rich and the spin of the hole is generous, a narrow beam can pierce the cocoon of accreting gas and point almost at the observer. Then the transient hardens. High-energy photons arrive in brittle cascades. Radio afterglows spread as the jet decelerates in the ambient medium. The timescale stretches from days to months. The black hole that normally ignores human clocks writes an event in the language of a season. In quieter cases, the flare remains thermal, its temperature hovering near tens of thousands of Kelvin, a hot ember receding into twilight. Planets are not exempt. A gas giant that meanders into reach will be stripped of its atmosphere first, leaving a core that suffers a later demise. Rocky worlds tear into fragments that vaporize as their silicates and metals face temperatures they were never meant to endure. The gas produced is rich in elements that seldom dominate astrophysical spectra. Calcium, magnesium, iron, and silicon stain the light with unusual shades. Such disruptions can happen not only around supermassive black holes but also around white dwarfs and neutron stars, stepping down the ladder of gravity while repeating the recipe with different outcomes. An asteroid that meets a white dwarf at the wrong speed becomes a ring of dust that later rains onto the surface, polluting the atmosphere and advertising the fate of a planetary system that once orbited in peace. A separate theatre opens for compact stars confronting intermediate mass black holes. A white dwarf that ventures too near can be squeezed so abruptly that its density and temperature spike into regimes where carbon or helium ignites. Nuclear burning then joins gravity's work. The outcome is a burst that mixes thermonuclear light with the signature of tidal unmakings. For the shortest passages, gravitational wave bursts whisper alongside the flare, though at frequencies that challenge current ears. The palette widens, and the terror acquires nuance. Tides do not only dismantle, they can force a star to burn itself while being torn apart. Not every victim arrives from a calm background. In dense nuclear star clusters, random scattering and resonant relaxation change orbits over time, nudging stars into the loss cone that feeds the black hole. Binaries supply a special conduit. When a pair strays close, one member can be trapped while the other is kicked free at tremendous speed. The refugee escapes as a hypervelocity star, and its former partner begins a life of tight orbits that may end in a future disruption or in a steady mass transfer if the black hole is of modest size. The population of fast exiles and tight prisoners speaks for this exchange. It is the social life of tides, written in statistics. There is geometry in the light. If the disk that forms is tilted, or the stream intersects itself at an angle that favors vertical structure, the photosphere can take on layers. Observers watching from different inclinations see different shows. Edge-on views encounter dust and wind and read the story through absorption and scattered light. Face-on views see deeper, down to the thermal engine that glows from the inner ring. Polarization, modest but telling, rotates as the system evolves, like a compass that swings while the wreckage settles. Outflows loaded with line-driving opacity carry not only energy, but also momentum that clears channels through which later photons travel more freely. The flare writes its own visibility into the environment as it fades. The math that predicts these scenes is plain and merciless. Tidal acceleration scales with mass of the black hole and with inverse cube of distance. Internal gravity inside the star falls with radius and depends on its density profile. Where one curve crosses the other, strength wins and cohesion loses. Penetration is measured by a parameter that compares the pericenter to the disruption radius. Deeper encounters yield faster fallback and brighter peaks, but relativity adds a twist. Strong precession at close passes can bend the stream completely, bringing it back to the collision point with terrible precision. Circularization quickens, and the rise to brightness steepens. Observers see this as a shorter path to fever, and as a flare that reaches high before the power law decline begins. Even in the most eloquent cases, a portion of the ribbon escapes. The unbound debris leaves the encounter on hyperbolic paths that carry fingerprints of the star's interior. Material that started in the outer layers tends to leave with different speeds than material that began deeper inside. If the star had evolved, the pattern encodes that evolution. The galaxy receives this debris as a breath enriched with elements that took millions of years to forge. The black hole eats only part of what it unmade. The rest becomes a traveling memory of the star in the medium through which it once quietly orbited. The emotional register of such an event is not gore but anatomy revealed. A star that hid its core behind a photosphere becomes a cross-section hung in space, its layers stretched and blended until chemistry and dynamics are inseparable. The flare is bright, not because a star chose to shine, but because structure failed. The lesson is the same from planets to giants. Tides take identity and convert it into sequence. Gravity, patient and exact, needs no contact, only closeness. Bodies approach, and bodies become lines. The lines fold into rings, the rings warm and breathe. Then the warmth fades and the night closes again. Somewhere far away, the star's name continues in a curve on a plot, a cool arc that descends with mathematical grace while the black hole sits unchanged, having only deepened its silence by an amount measured in the mass of something that once had surface and weather and time. A horizon invites a question that feels simple at first. If nothing returns, what becomes of the details of what goes in? A star does not carry only mass and charge and spin, it carries a history. every photon it absorbed, every nuance of its interior currents. When that star fades into a black aperture, the exterior world can weigh the addition and notice the conserved quantities that survive. Yet the fine print disappears from view. The tension begins here. Physics insists that evolution is unitary at the deepest level. Quantum states change in ways that preserve information. If a black hole erases detail, then the book of nature has missing pages. That loss would break a rule more sacred than any symmetry of coordinates. Thermodynamics arrived first to make mischief. An object with an event horizon seems to have a one-way boundary that can only grow. If two such objects meet, the area of the combined horizon is not smaller than the sum of the areas that came before. The analogy to entropy is obvious. In ordinary systems, entropy measures the number of ways a state can be arranged without changing what we can measure from outside. The second law of thermodynamics says entropy does not diminish for closed systems. At this border of gravity, an area law appears to echo that command. The echo grows louder when the smallest quantum corrections are allowed. A black hole has a temperature. It emits radiation as if a tiny furnace lives on the horizon. The temperature is inversely proportional to the mass. The larger the hole, the colder the glow. This radiation does not carry any visible imprint of what fell in. It looks thermal. It looks like amnesia in the form of heat. If a black hole radiates, it must shrink unless fed. Shrinking would decrease area and therefore decrease the entropy written on the horizon. General entropy must therefore include both the area term and the entropy of the radiation outside. The sum must not fall for any process. The bookkeepers of the universe obey that balance, yet a deeper account remains unsettled. If the glow is purely thermal, then as the black hole evaporates, the outside world collects featureless heat and the interior dwindles to nothing. At the very end, there is no place left to store what had been swallowed. Unitarity would fail. A long argument then unfurls. Either unitarity is less absolute than believed, or the radiation is not fully thermal. The second option requires correlations in the outgoing light that encode the original data in disguised form. Entropy counts microstates. If the horizon carries an area law, then the number of states should grow exponentially with area. What are those states? They do not live inside in any simple sense because nothing inside can return to share its count. They must be degrees of freedom associated with the boundary of causality itself. Ideas flower here. Some imagine quantum bits tied to soft modes of the gravitational field that extend to null infinity. Soft hair on a black hole would then store the data in gentle ripples rather than in violent structure. Others propose that the bookkeeping does not live on the horizon but instead on a surface at infinity. The holographic impulse takes this further. It asserts that the data describing a region with gravity can be equivalently encoded on a boundary with one less dimension where gravity can be replaced by a quantum field theory that evolves without leaks. If such an equivalence holds, then a black hole is a thermal state in that boundary theory, and its formation and evaporation are perfectly unitary processes. The paradox shifts into a difference of languages. One can tell the story in the bulk and stare at a horizon that seems to consume truth, or one can tell it on the boundary and watch a bath of excitations that evolve with impeccable memory. Translation rules must then guarantee that no contradiction survives. The exterior observer never sees information vanish. The interior narrative becomes an effective picture that omits details the boundary keeps safe. Firewalls enter as an audacious proposal born of logic cornered. Quantum mechanics grants entanglement. Modes just outside the horizon are entangled with modes that live just inside in the vacuum state expected by anyone who falls freely through the edge. During evaporation, however, modes that have already left on earlier days remain entangled with yet newer radiation in order to keep the long-term evolution unitary. A single quantum cannot be maximally entangled with two independent partners. This constraint seems to force a choice: preserve the gentle crossing for an infalling observer and abandon unitarity, or keep unitarity and shred the entanglement across the horizon. Shredding would replace the smooth vacuum with a high-energy curtain. An infalling traveler would burn in a flash of quanta at the very threshold. The suggestion is drastic. It breaks a cherished expectation of equivalence between a local inertial frame and empty space. Complementarity attempts to soften the blow. It argues that no single observer ever experiences both sides of the alleged conflict. A distant astronomer can decode the radiation and recover the data in principle given patience and resources that border on the absurd. An infaller experiences a serene crossing and then follows a trajectory into regions no outside agent can interrogate. No contradiction occurs because nature does not allow one agent to compare notes along both pathways. The two stories are dual descriptions built for different viewpoints. They are consistent if told with proper limits. The paradox then deflates not by demolishing any rule, but by refusing to place incompatible measurements in the same frame. A more recent set of calculations adds contour to the debate with a sketch of the entropy of radiation as a function of time. At first, as the whole radiates thermally, the entropy of the exterior bath grows. Later, if information begins to leak out in subtle correlations, the entropy must peak and then decline towards zero as the radiation comes to encode the entire initial state. The curve that rises and falls in this way is called the Page curve. Reproducing that curve from within gravity requires new tools. Quantum corrections to the formula for entropy introduce candidates called islands. These are regions in the interior that are included in the entanglement wedge of the exterior radiation after certain times. Put differently, the degrees of freedom in those islands are counted as part of the radiation for the purpose of entropy. This counterintuitive step yields a Page curve that turns down at the right moment. It suggests a rule for assigning which pieces of the geometry are owned by which sets of quanta when entanglement is the currency. No single image has yet stilled the arguments. Some propose that wormholes link distant quanta in ways that turn entanglement into a geometric bridge. The phrase that unites this idea is brief and enigmatic. Einstein-Rosen equals Einstein-Podolsky-Rosen. A non-traversable wormhole would then be the bulk avatar of mere quantum correlation on the boundary. In such a picture, decoding information from Hawking radiation might be represented by complex manipulations that effectively open a path through the geometry. The traverse is metaphorical. No signal moves faster than light. Yet the act of reconstruction gains a spatial intuition in a language that knows how to think with lengths and areas. The spectral character of Hawking quanta is itself a clue that knowledge hides in almost invisible fine structure. Perfect thermality would erase distinctions. Any departure advertises a pattern. Correlations that matter will be almost unimaginably delicate, like a watermark hidden in the grain of paper rather than printed in ink. Practical recovery may remain impossible for macroscopic holes. The principle matters more than any experiment here. Nature must choose a rule set that keeps unitarity and honors the experience of smooth crossing as long as curvatures are not yet Planckian. A failure would stain more than black hole theory. It would shake the faith that the sum of all processes retains the details of its beginnings, even when thousands of interactions rearrange the surface. Entropy as area raises its own metaphysical quiet. Why is the count two-dimensional when the object is three-dimensional? The hint mothers a vision in which space-time itself emerges from entanglement. Connectivity is then not merely a map drawn on a pre-existing sheet. It is the sheet. Where entanglement weakens, space stretches. Where it breaks, space fractures. In this view, a horizon is a place where patterns of quantum links reorganize in a way that prevents certain reconstructions for certain observers. The whole is a failure of access, not a place filled with exotic matter. Terror then shifts from the image of a singular core to the possibility that reality is a weave whose threads tie information to geometry so tightly that asking for one without the other becomes meaningless. None of these ideas diminishes the awe of classical pictures. They add a second layer where heat, probability, and quantum memory infiltrate a landscape once drawn only with curvature and geodesics. The brink becomes a laboratory for thought experiments that stretch minds and equations to their limits. Whether the final synthesis will resemble soft hair catalogues or island rules, or a tapestry of equivalences between bulk and boundary, is not yet resolved. What strengthens with each attempt is the conviction that darkness is not empty. It is coded. The code is not inked on a surface anyone can touch. It is embedded in correlations that lace the universe together. To watch a black hole form and fade is therefore to watch a transfer between lexicons. Bits become arcs of light. Arcs become heat. Heat becomes correlated, whispers that only a perfect patience could decipher. A horizon is a promise that nature can hide without forgetting. Space does not ring like air, yet it can carry a tremor that behaves like sound. Two black holes close a dance that has lasted for ages, and the fabric itself loosens a sigh. The signal begins in whispers far below human hearing, then climbs as the orbit tightens, a rising chirp that carries mass in its pitch and distance in its volume. Interferometers stretch lasers across kilometers and teach mirrors to listen for changes smaller than a proton's width. When the wave arrives, arms lengthen and shorten in alternation, and the instrument writes that change is a trace of light. The trace is not dramatic to the eye, but within it a pair of horizons is born into one. The physics of the song is spare and stern. Gravity waves carry energy, so orbits decay. Binary black holes lose height in the potential until the last few circles complete in a rush, velocities touching a significant fraction of light speed. The chirp holds three movements. In-spiral is the patient climb in frequency, a metronome that accelerates as distance shrinks. Merger is the brief crescendo when the horizons touch and interleave. Ringdown is the fading tone of the new object settling toward quiet, its geometry vibrating with a handful of natural frequencies that depend only on mass and spin. These stages let observers weigh darkness by timing alone, and never before did timing offer so complete a portrait of events no light will ever see. Waveform models sharpen the ear. The equations of general relativity do not yield simple closed forms for all phases, but approximations and numerical solutions together compose a library of possible songs. Matched filtering compares the data to this library and pulls out signals that hide below noise. The best match returns parameters with uncertainties that can be written down. Masses arrive, both in the detector frame and translated to the frame of the source after accounting for redshift. Spins appear as vectors, with magnitudes and tilts relative to the orbital plane. Sky position emerges as an arc or a patch, depending on how many instruments heard the event. Distance slides out of the amplitude, with help from the orientation of the system and the antenna patterns of the detectors. The first dozens of mergers revealed a population that surprised in detail. Component masses often fell in ranges that were thought rare based on prior observations of X-ray binaries. Some pairs were nearly equal, some unequal but not extreme. Spins in many events appeared modest and sometimes misaligned, hinting at formation channels where black holes did not have time to align with their disks, or where dynamical interactions in clusters threw pairs together late. A few signals hinted at the spin of the final object precessing the orbital plane during in-spiral, a slow wobble that modulates the phase and amplitude of the wave. The catalogue expanded in small storms of announcements, and with each addition the statistics grew more articulate about how black holes find one another. Mass gaps, once theoretical curiosities, met data. Above a certain range, stellar evolution predicts that pair instability should prevent the formation of black holes by direct collapse due to explosive episodes that unbind the star. Finding components apparently inside or beyond that desert suggested two-step histories. A smaller black hole might have merged with another and then joined a new partner, climbing the ladder into forbidden territory. Alternatively, low metallicity progenitors could have skirted the boundaries of the theory. The waveforms could not adjudicate alone, but they pointed where stellar physics must revise its chart. Intermediate mass systems approached audibility with heavier voices. When total mass rises into hundreds of suns, the in-spiral spends fewer cycles in the sensitive band of ground detectors. The signal becomes a shorter thump with a strong merger and ringdown. Identifying such events requires templates built from numerical relativity, and confidence deepens when the ringdown exhibits a dominant mode matched by subdominant overtones. The presence of harmonics and higher multipoles extends the diagnostic power. Deviations from the simplest quadrupole pattern enrich the shape of the chirp and carry information about asymmetry and inclination. Tests of gravity unfold in the tail of the song. The ring-down modes form a spectrum that should be determined uniquely by the mass and spin if the final object is a black hole of the Kerr family. Measuring more than one mode allows a test of that uniqueness, sometimes called black hole spectroscopy. Agreement supports the theory. Disagreement would have profound implications. Bounds on dispersion of gravitational waves, limits on graviton mass if one were to exist, and constraints on Lorentz violating effects emerge as byproducts of careful fits to time and phase. Every event becomes a laboratory, and the laboratory improves when more ears are open and more bandwidth is clear. A separate orchestra plays at longer periods. Supermassive black hole binaries produce waves with wavelengths measured in light years. Terrestrial interferometers are deaf to such notes. Pulsar timing arrays step in as galactic clocks. Millisecond pulsars emit radio flashes with regularity that rivals atomic standards. A passing gravitational wave slightly changes the light travel time along the line of sight, imprinting correlated timing residuals across the sky. Patterns in those correlations sketch the spectrum of a background built from many binaries far away. Detection of this hum opens the door to a census of giants that have not yet merged, and to a study of how galaxies bring their hearts together in slow embraces. Between the ground and the pulsar, a space-based interferometer will patrol the millihertz band. There, the universe offers signals from mergers of massive black holes at cosmological distances and from extreme mass ratio inspirals where a compact star spirals for years into a supermassive partner. The latter write maps of the central potential with the precision of a planetary mission, each periastron passage adding a line to a chart of spacetime that no other method can draw. Environmental effects like gas drag or interactions with a surrounding star cluster can perturb the waveform, allowing inferences about the medium near the giant. The combination paints the centers of galaxies in a language that until recently had no instrument. Standard sirens turn gravitational waves into tools for cosmology. The amplitude of a binary signal gives a direct measurement of its luminosity distance, independent of the cosmic distance ladder. If an electromagnetic counterpart or a host galaxy identification supplies a redshift, the pair distance and redshift trace the expansion of the universe. When a neutron star participates, a kilonova or a short flash can point to the host. For black hole binaries, a statistical association with catalogs or the rare chance of a flare from a circumbinary disk may provide the missing piece. With enough events, the Hubble constant can be inferred, and the long argument about its value gains a new adjudicator. Mergers do not always follow quiet circular paths. Eccentricity can survive into the band when formation occurs dynamically. For example, in dense star clusters where capture happens during close passages that radiate enough energy to bind the pair. Eccentric signals carry harmonics that tint the waveform, and detecting them reveals a corner of the black hole's social life otherwise hidden. Lensing can also sculpt the song. If a massive object lies along the path, it can split or magnify the wave, creating repeated arrivals or distorted amplitudes. The effect tests both the gravitational wave propagation through curved spacetimes and the distribution of matter between us and the source. Memory adds a curious coda. Gravitational waves that pass can leave a permanent displacement in the positions of test masses, a slight change that does not relax after the wave has gone. This nonlinear effect is tiny for single events at current sensitivities, but for a background it may emerge as a global drift in timing or in the apparent shape of the detector response. The idea that space can remember a passing tremor fits the mood of black holes teaching the universe to keep accounts in very subtle ways. The enterprise of listening continues to refine itself. Squeezed light reduces quantum noise in the interferometers. Improved coatings and cryogenic designs quiet thermal jostling. Better seismic isolation deepens low-frequency reach. Networks expand and triangulate with greater precision, shrinking sky maps from swaths to islands where telescopes can search for counterparts quickly. Algorithms learn to sift data in near real time. Catalogs grow, not just in count but in diversity, and with them the ability to ask whether there are preferred masses, whether spins align more in one population than another, whether the rate of mergers follows star formation or the assembly of structure. What is terrifying is not loudness, but clarity. The waves carry no dust, suffer no scattering, and forget nothing about phase along the way. They travel straight through dark matter halos and galactic bulges, across voids and filaments, arriving with a fidelity that electromagnetic signals rarely achieve. They deliver the most intimate details of gravity's own machinery, the closing of horizons and the settling of a single, larger geometry. Astronomers once feared that the centers of galaxies would forever be hearsay. The universe found a way to let the centers speak, not with light but with rhythm. A collision billions of years and billions of light years away makes a laser in a quiet valley tremble for a breath. The tremble writes a line on a monitor. The line tells of mass, of spin, of a union that ended the separate lives of two curvatures. In that line, darkness is loud. A camera that can see a horizon cannot be built in any single dome. The aperture must be as large as Earth. The light must arrive not as a picture but as a whisper of phase measured at many mountaintops at once. The method is very long baseline interferometry. Dishes at deserts and on volcanoes, on plateaus and polar airfields, tune themselves to millimeter wavelengths where the glow from hot plasma near a black hole escapes the haze of interstellar absorption. Each site drinks the same wavefront and timestamps it with an atomic clock so precise that a slip of a few trillionths of a second would blur the vision. Hard drives store rivers of bits. Weather forecasts become as important as textbook equations because a cloud above just one dish can erase a piece of the eye. When the observing window opens, the network moves as a single instrument. Signals ride to shore on microwaves and fiber loops inside each facility, then freeze in metal cases that will later travel by aircraft to a central place where they can be made to interfere. Correlators align the data by sliding it in time until fringes appear, patterns of constructive and destructive overlap that contain the image in coded form. The planet has become a lens. The beam of that lens is not glass but geometry. Each pair of dishes defines a baseline that samples one spatial frequency of the scene. Longer baselines respond to finer detail. As the Earth turns, baselines rotate and trace arcs through UV space, where spatial information lives. After a night, the collection of arcs becomes a sparse constellation of samples. From those points, an image can be rebuilt. The reconstruction is not a simple inversion. Noise, atmospheric phase jitter, and calibration uncertainties conspire to make the problem ill-posed. Closure quantities rescue the effort. Closure phase sums the measured phases around a triangle of baselines to produce a number immune to the distortions of the individual stations. Closure amplitude forms combinations of measured strengths that shrug off gain errors. These closure observables carry the robust essence of the source, the part that the sky truly owns. Imaging algorithms then search for a brightness distribution on the sky that reproduces the closure data and the visibilities within tolerances while obeying gentle expectations about smoothness, compactness, and positivity. Different teams try different regularizers and priors, creating families of reconstructions that agree where the data are ironclad and diverge only at the fringe. A nearby giant offers the first portrait. The engine sits at the center of an elliptical galaxy embedded in a bright cluster. Its mass counts in billions of suns. At millimeter wavelengths, the glow from the inner accretion flow begins to resolve into a ring. Not a perfect circle, not a rigid hoop, but a crescent weighted to one side, where plasma approaches the observer and beaming brightens the arc. The diameter of the dark central region is set by mass and distance. It is larger than the simple crossing of the last stable orbit would suggest because the photon paths bend and hover before committing to escape. The ring is the contour of those hesitant photons. Its size delivers the weight of the black hole without touching it, and its near circularity supports the classic geometry of general relativity in a place where curvature is absolute. Polarization maps add a layer that looks like weather drawn on fire. Light remembers the orientation of the electromagnetic field when it was born. As it travels through magnetized plasma, Faraday rotation twists that memory. At millimeter wavelengths along this sightline, the twist is moderate. The polarization vectors can therefore sketch the magnetic structure near the emission region. They curl around the ring and align along the jet axis, implying an ordered field that threads the inner accretion flow and helps launch the outflow. The picture is not only a silhouette, it is a glimpse of the engine's wiring. A second target reveals a different difficulty. The mass is only a few million suns and sits much closer. The shadow is larger on the sky than the distant giant, but the plasma near it evolves on timescales of minutes. The image is a moving target. Interstellar electrons between Earth and the center of the galaxy scatter the wavefront into a blurry, twinkling smear, like starlight seen through ripples in hot air above a road. To recover the shape beneath the shimmer, observers model the scattering as a convolution that can be partially reversed, and they assemble many short exposures into a statistical portrait. The result keeps the ring, yet shows that its brightness flickers and the arc shifts as the flow tumbles. A movie in slow motion replaces a single still. The camera must choose between crispness and honesty about time. Every element of the instrument carries romance and rigor. Hydrogen masers serve as local clocks, their steady song-holding phase across continents. Cryogenic receivers cool their own noise until the sky's whisper dominates. Calibration tones are injected and measured. Pointing models and focus curves are tested against bright, compact quasars that act as reference beacons. When a dish joins the network for the first time, its success is celebrated like a new eye-opening on a creature that has learned to keep its gaze steady while turning its head. Data volume reaches scales that cannot cross oceans by network. Rugged disks travel by hand from high sites to sea level, then fly across time zones. A correlator racks them in rooms that hum and glow. Engineers tune delay models to account for tectonic motion, earth tides, polar wobble, and even loading from air pressure that slightly deforms the surface under a station. The last nanoseconds of misalignment drop away, and fringes resolve into confidence that every piece of the planet-sized lens saw the same thing. Imaging does not deliver only one answer. It delivers many that agree in their essentials. To prevent wishes from painting the scene, image challenges are staged using synthetic data for hidden sources. Teams reconstruct blind and check whether methods fall for common traps. The algorithms are made to fight for humility. When real data finally clear the gauntlet, the ring that emerges is not a surprise created by hope. It is the stubborn remainder after doubt has been given every advantage. Astrophysical interpretation needs translation from picture to physics. Radiatively inefficient accretion flows, magnetically arrested states, and jet launching models are forward modeled to predict brightness distributions and polarization structures. These models are blurred by the sampling and scattering of the instrument, then compared to the observation's enclosure space rather than only an image space. Fitts return rules about electron temperature ratios, magnetic pressure, and the balance between disk and jet emission near the horizon. The sketch of the silhouette becomes a parameter study for the conditions that give it edge and flame. Mass measurements from the ring diameter align with those obtained by stellar orbits or gas dynamics, with uncertainties slimmer where the distance is known best. Spin remains more elusive because light distribution depends on thermodynamics and magnetic geometry, as well as on the location of the last stable orbit. Polarization and jet collimation help, but degeneracies persist. Time variability adds leverage. If features sweep around the ring with a period set by orbital motion near the inner edge, the timescale anchors the gravitational radius more tightly and reveals whether the spacetime is viewed more face-on or more edge-on. Future eyes grow more ambitious. Additional dishes fill gaps in spatial frequency coverage, reducing the need for priors. New receivers push to slightly shorter wavelengths, where scattering softens and where the photosphere sits closer to the last orbit. Space antennas in a high orbit could join the network, extending baselines beyond Earth's diameter and resolving substructure within the crescent. With longer campaigns, movies will replace portraits as standard products, showing hotspots that ride the flow, and perhaps witnessing transient launch events when magnetic fields reconnect and hurl plasma into the jet. Polarimetry will sharpen and separate rotation from turbulence, teaching which regions carry ordered flux and which shower the light with random twists. Coordinated campaigns across the spectrum turn a silhouette into a chapter within a thick book. X-ray telescopes watch the corona brighten or fade, while millimeter eyes see the ring keep its size. Infrared light records hot knots as they orbit. Radio arrays farther down in frequency map the jet as it expands and cools. Each band has a clock with a different tick rate. Aligning their ticks reveals causal connections. A flare in the inner flow might precede a change down the jet by a predictable delay. Patterns like this convert a static curve into a story with cause and effect. There is also a use that borders on the philosophical. Gravity's equations are precise and unforgiving. They predict that the shape of a shadow should follow general rules nearly independent of the details of the plasma. Deviations beyond tight bounds would hint at new physics. The measured ring diameter, its slight displacement due to lensing and spin, its asymmetry, and the brightness gradient across it, all can be written as constraints on the space-time metric. No exotic modification is suggested by the current portraits. The absence of surprise becomes a quiet affirmation that the same rules that curve starlight at the rim of a galaxy also sculpt the glow at the rim of an event horizon. A human eye cannot truly look through this instrument, yet the mind insists on translating the reconstruction into sight. The dark middle is not a hole cut out by artists. It is the projection of a region where photons cannot arrive from behind because their paths were bent away or trapped. The ring is not a flame. It is a census of last chances, a count of photons that skimmed a curved path so finely that a fraction escaped. The asymmetry is not a smear. It is the stamp of motion, the approaching side praising itself in brighter tones, while the receding side withdraws into redder, quiet. To watch this is to realize that vision can be built from patience and geometry as much as from lenses and glass. An image of a shadow is a paradox in words, but the universe holds it steady long enough for Earth to blink and understand. A galaxy is not a city that builds in peace and then hires a furnace to keep it warm. It is a living agreement between a crowded sky of stars and a single, silent core. The pact begins with gravity collecting gas into a halo that cools and rains toward a disk. There, clouds fracture and hide blue embers that become suns. Yet the center keeps an account. As the nucleus feeds, it repays the inflow with energy cast outward, as light, as wind, and as a pair of narrow spears that aim for the edges of the halo. The balance between birth and warning settles into a rhythm that writes the colors and shapes of galaxies. Within bulges, old stars shuffle in slow orbits that carry the memory of past upheavals. Their random motions scale with the weight of the central object. The greater the dispersion, the heavier the unseen mass. A relation holds as if a signature had been signed across millions of light years. The heavier the heart, the harder the bulge breathes. At first glance, the link seems unlikely. The black hole is smaller than a grain of dust when compared to the galaxy. Yet the signature persists. The central engine is a valve on the pressure of star formation. When it opens and pours energy into the surrounding medium, gas loses the will to clump. When it closes for a time, clouds assemble and the city glows with new neighborhoods. There are two temperaments in this influence. One is bright and brief. As the engine shines like a beacon in the visible and ultraviolet, lines in the spectrum blow blueward, evidence for winds that race from the nucleus faster than any storm in the interstellar weather that came before. Those winds carry momentum and heat. They ram against the inner gas and drive shocks that loosen the grip of gravity on the next generation of stars. The other temperament is quiet and persistent. The nucleus launches jets that travel with near-perfect aim, inflating bubbles in the hot halo gas of groups and clusters. The bubbles rise gently like lanterns and yank on the atmosphere behind them, stirring and heating it so that the long cooling the halo desires is interrupted again and again. The galaxy remains red and still because the nucleus keeps reminding it to delay. Coupling is the key. Energy must find the parts of the galaxy that would otherwise make stars and persuade them to slow. If photons do the work, they push dust grains that share their force with gas. If winds do the work, they carry a dense shell that snowplows material into a wave. If jets do the work, they deposit heat where the gas would have condensed, lifting entropy and flattening temperature gradients. In each case, the coupling efficiency is the number that matters, too weak, and the galaxy forms too many stars and violates the census of old systems observed in the sky. Too strong, and the galaxy loses its gas in a tantrum that leaves it smaller than its peers. Nature appears to have found a middle path, with flickers of activity that add up to a stable climate when averaged over millions of years. The pact is not uniform across mass. Small halos lose gas easily to supernovae and gentle winds. Very large halos trap heat and confine the interstellar medium within deep potentials. In those giants, feedback from the nucleus is the adult in the room. Without it, clusters would cool and collapse into fireworks that never dim. With it, sound waves ripple through the atmosphere, cavities fill and detach, and filaments condense only where turbulence and uplift permit. Precipitation models imagine a threshold where cooling times fall below a multiple of the free fall time. At that threshold, clouds form and drift inward, feeding the center enough to launch a response that reheats the gas and raises the ratio again. The halo and the heart regulate one another through a thermostat that needs no hand. Star formation listens. When inflow builds up in the inner kiloparsec, gas compacts and the surface density rises. A burst lights up the bulge and drains the reservoir that fed it. At the same time, the nucleus awakens and spends energy that puffs the gas and thickens the disk. The burst fades. New inflow tries again. The cycle repeats with different intervals depending on the ease with which angular momentum can be shed. Bars within disks act as ladders, moving gas inward one rung at a time, while also creating shocks that heat and disperse clouds. The center responds to these deliveries with pulses that have distinct signatures. A quasar phase leaves a scorched, metal-rich wind and a sudden drop in cool gas. A radio-loud phase leaves bubbles and sound, where the halo needed to forget how to condense. Observers read the pact in demographics. Blue galaxies glow with youth, but cluster less in the most massive environments. Red and quiescent galaxies hold their numbers where halos are deep. Morphology shifts with environment too. Disks thrive in the field. Spheroids fill the centers of groups. The central engines in those spheroids are often quiet in light, yet loud in influence, their jets carving cavities in hot atmospheres visible across hundreds of thousands of light years. Where the radio ghosts hang, the rate of star formation is curtailed. The outline of the agreement is written not in one image, but across the entire map of galaxy kinds. The agreement also sculpts chemistry. Winds lift heavy elements from star-forming zones and distribute them through halos and intergalactic filaments. Metallicity gradients flatten when the nucleus triggers fountains that carry gas up and let it rain back down. The returning flow seeds new stars with a more uniform mix of elements, softening distinctions between inner and outer neighborhoods. In dwarfs, metals escape outright and leave thin soups behind. In giants, metals collect in the atmosphere and mark where energy has passed. The black hole, therefore, acts not only as a heater, but as a blender, stirring the flavors of the galaxy. Duty cycles create the rhythm. The engine does not stay on. Instead, it flickers across orders of magnitude in power on timescales that range from months in its innermost regions to millions of years in its broader weather. The galaxy experiences these flickers as seasons: a long winter of suppression, a shorter spring of compaction, a summer of storms, then a fall of gentle settling. The sum of the seasons matches the slow drift from blue to red that surveys reveal over cosmic time. 1 billion small choices in accretion add up to a few grand outcomes: a star-forming disk, a quiescent spheroid, or a hybrid that shuffles between the two. In clusters, the pact becomes a civic project. The central galaxy sits in a bath of hot plasma that would cool catastrophically without intervention. Jets from the nucleus inflate cavities whose rims host filaments of cold gas. The filaments sink and feed the engine again. The energy budget balances within a factor of a few. A minor difference would produce either a snowstorm or a desert. The match suggests that the nucleus senses its environment with a crude but effective feel for need. In reality, the sensing is automatic. Fuel supply reflects the state of the atmosphere. The engine responds only to what it is given, but that response changes the next delivery. The loop closes without intelligence and yet performs like memory. At higher redshift, the pact shifts its accent. Gas fractions are higher, disks are clumpier, and inflow along cosmic filaments is more vigorous. The nuclei shine more often and more brightly. Quasar winds sculpt young galaxies, building spheroids quickly, and drawing a line between systems that will join the red sequence and those that will remain blue. Outflows carry dust and molecules to distances where the halo wind cools and forms new clouds that may later fall. The cycle becomes large, extending beyond the office of the nucleus into the corporate campus of the circumgalactic medium. The halos remember these events through column densities and temperatures that can be read with ultraviolet and X-ray eyes. The pact has left receipts all the way to the edge of the gravitational lease. Recoiling remnants write editorials in this civic history. A black hole shoved from the center by an asymmetric merger does not keep feeding the heart of the galaxy in the usual way. Its off-center accretion lights a second lamp and stirs stellar orbits in a halo of confusion. When it returns, the core bears a scoured profile without a dense cusp. The history of these excursions is carved into light profiles and star kinematics. Even without a visible outburst, the pact is legible in the architecture it leaves behind. There is a cost in all of this that is counted in futures. Feedback prevents some stars from ever forming. The light that would have shone is never made. Yet the cost is what allows the universe to build long-lived structures. Without restraint, fuel would burn too swiftly and leave galaxies exhausted. With restraint, stars form slowly and fill the deep time available. Globular clusters age beside their hosts. Planetary systems orbit in stable potentials that do not change their moods every few 100 million years. The center keeps the periphery calm by choosing moments of discipline. The most disquieting truth in the pact is that small causes can govern grand scales. A radius measured in light hours decides climates measured in tens of thousands of light years. The conversion from one scale to the other travels through fluids, fields, and shocks. It leverages the leverage of gravity itself. A thin jet entangles a whole atmosphere. A shell of wind catches an entire disk. The pact needs no bureaucracy. It is signed in physics, honored by the momentum of outflows, and filed in the entropy of halos. What remains to be learned are the margins where this agreement fails or is rewritten. Some galaxies ignore the script and bloom with stars despite an active center. Others remain quenched longer than models predict. The missing details likely hide in geometry and timing, the angle of a jet relative to dense filaments, the layering of dust that shields one cloud but not another. The coincidence of a bar forming at the same time a fountain returns. The broad rule endures. The central engine and its host do not live separate lives. They share a budget, argue about expenditures through wind and light, and reach a compromise that endures for ages. The city and its furnace thrive because they are one organism divided by scale. Time stretches when gravity is deep, and future stretches when thought is patient. In the far reaches of possibility, black holes do not remain only engines of present violence. They become the trustees of energy and the archivists of matter. Galaxies will fade. Star formation will thin as gas is locked into long-lived embers or lost to slow winds that never return. The brightest beacons will dim to a sparse confetti of red dwarfs and white embers, yet the centers will endure, heavier than their hosts, quietly pulling in whatever strays. The long biography of the cosmos tilts toward a chapter where darkness is not a backdrop, but the actor with the last lines. Stars have clocks dictated by mass. Giants burn quickly and depart as neutron remnants or smaller holes. Dwarfs sip their fuel and can glow for trillions of years. Eventually, even these thrift shops of fusion sputter, with no fresh supply of cold gas. Galaxies become museums of orbits. Black holes continue to gather. Stellar remnants drift inward through friction with stars and dark matter. Binary encounters sling the lightest objects away, and drop the heaviest toward the abyss. The center grows by meals that are small compared to its mass, but steady on scales that forget human comparisons. The universe, once talkative with the light of birth, moves into a quieter phase where gravity shades into bookkeeping. Remnants will meet remnants. Stellar mass black holes in old clusters exchange partners and form binaries that decay through gravitational radiation. Each merger transfers a little energy from orbit to space-time and a lot of mass from two small horizons to one larger one. Supermassive cores will collect uncounted of these ancient unions as decayed clusters deliver their compact cargoes into the inner parsec. With each arrival, the spin and mass ledger changes. Sometimes the spin will ease, sometimes it will sharpen, depending on angles that have long forgotten their origins. The centers will become palimpsests of merged histories, written in parameters that no longer carry the specifics of the stars that began the story. A new era arrives when burning ends. Brown dwarfs, rogue planets, and cold white dwarfs feel a statistical tug toward central wells as occasional encounters reshape orbits. The pace is glacial, but the clock is generous. Some worlds will spiral into intermediate mass black holes if such objects persist in dwarf halos and ancient clusters. Others will skim close enough to be unmade. The chemistry of these meals will be muted by low temperatures and long times, yet the physics remains clear. Tides will pull apart what binding energies allow, and fragments will drizzle into the horizon like sand pouring from a patient hand. On timescales so long that naming them is an exercise in humility, even the quietest holes are not entirely silent. Quantum fields near horizons do not rest. Pairs appear for a moment, and in the presence of a boundary that hides, the balance between creation and annihilation shifts. An outside observer sees a faint thermal glow, a temperature inversely tied to mass. For the supermassive, that temperature is colder than any natural background today. Only when the universe expands into thinness and any remaining starlight is redshifted into insignificance will that faint glow stand alone. The large holes will be last to feel it. Stellar mass holes will evaporate after spans that make geological time feel like a blink. Giants will take longer than any countable history, radiating their mass into a rain of photons and light particles that carry away the memory of curvature. Evaporation is not a single effect, but a slow arithmetic done at the edge. Each quantum carries energy, and energy comes from mass. As the mass decreases, the temperature rises. Near the end, the glow turns from chill embers into a brief flare before arithmetic runs out. Whether the final stanza ends in a smooth fade or a last punctuation depends on details still debated. The census of light particles at those energies, the behavior of gravity at scales smaller than any current probe, the fate of information encoded in correlations too delicate for any practical ear. In all plausible paths, the horizon will shrink to nothing. The census of black holes will approach zero, and the universe will inherit the residue of all that once fell. Before that end, long periods of equilibrium will exist in which the mass of a black hole is not altered by evaporation, because the surrounding background is warmer. As the cosmos expands, temperature falls. One by one, horizons cross the balance point where their glow dominates their intake. The switch is a quiet event, like a heater clicking on in a house no one occupies. If any structures still feed the whole at that epoch, their contributions will be sparse. The cosmic medium will have thinned to a nearly perfect vacuum. The last feasts will be the slow capture of wandering remnants whose orbits stretched with each flicker of gravity and each small encounter over ages beyond counting. Some futures imagine matter decaying on its own long ladders. Protons, if unstable, would leak their identities into positrons and neutrinos, plus soft radiation after lengths of time beyond any star's patience. If this decay is real, then the warehouses of cold matter, planets, and the cinders of giants will unravel into a rarefied sea. If protons are eternal, the cosmos will carry relics of chemistry into depths of age that make black hole lifetimes less lonely. Either path leaves the black holes as anchors. They dictate the late heating and the final return of mass to radiation. Dark matter, if it consists of stable particles that rarely speak to baryons except through gravity, will join the late migration. Some will fall into halos within halos, and then into the deepest wells where only curvature convinces. Accretion of such quiet matter does not blaze, it simply deepens the well. If dark matter is made of lighter quanta that behave collectively, waves rather than marbles, then interference patterns might set the pace of late capture in ways that only maps of phase space can tell. Regardless of the identity of the dark, the ultimate accountant remains gravity, and gravity prefers minima. On any map that draws histories with fidelity, black holes become the main repositories of low entropy in the late universe. While stars and planets rearrange their heat into gentle gradients that are easy to reverse only in theory, horizons store information as area. Their entropy is vast, dwarfing that of any ordinary matter at similar mass. When these storehouses vanish through quantum leakage, they return an even vaster number of low-energy quanta, distributed so sparsely that no concentrated structure remains. The overall entropy of the cosmos continues to climb to values that mock intuition. Order that once took shape in spirals, bars, clusters, and molecular clouds becomes a trace dissolved in evenness. Speculation can lean farther. If the metric of spacetime is not the last word, if new fields awaken when densities or curvatures cross thresholds unknown, then late epochs could host transitions that redraft the landscape. Scalar fields might roll, changing the vacuum energy and driving new acceleration. Couplings might drift, altering how light moves or how masses weigh one another. In most such fantasies, the rule remains that any localized store of energy will either disperse or be captured by a horizon and then disperse later as radiation. Black holes remain the last brokers of how concentration ends. Even in a heat death where temperature approaches uniformity and gradients vanish, memory does not become impossible. Quantum fluctuations persist, though the timescales for any macroscopic fluctuation become beyond imagination. Rare events are not forbidden, only improbable to the point of indifference. A stray patch of lower entropy could briefly congeal into complexity, then dissolve again. Such blips cannot carry a narrative. They cannot sequence their own cause and effect reliably against the pressure of the averages. The last meaningful stories are the predictable ones: the fade of stars, the mergers of horizons, the slow cooling of a sky that no longer has edges of contrast to catch the eye. What remains haunting is the role of scale. The strongest curvatures today live near horizons measured in microseconds and hours, yet their decisions hold sway across epochs that stretch beyond any ordinary language. A ring of gravity focuses a city's weather now, and a cluster's weather later. Then, in ages that avoid names, it decides how the universe returns its mass to the background. Silence in the end is not a moral, but a boundary condition. With no gradients left to animate processes, time loses the asymmetry we used to read in every flame and every orbit. Only weak interactions and long correlations remain, fading like echoes in a canyon after the shout has scattered. The picture is austere, but not bleak. Beauty lies in how a few equations, written in the geometry of curvature and the arithmetic of quanta, guide a cosmos from a hot beginning to a thin conclusion without losing discipline. The largest black holes, terrifying in youth, become guardians in age. They tidy the ledger of mass and return what they borrowed as diffuse light. They are monuments to the idea that nature conserves, translates, and eventually disperses. They do not choose their role. Geometry assigns it. The night ahead is long. In that night, gravity holds a vigil, and when the fire is out, it will carry the last heat to the cold until the difference is gone. There is a place where questions approach a shore they cannot cross. It is not a wall, not a cliff, not a gate carved by any hand. It is a contour drawn by equations where time leans inward and light forgets how to climb. An observer can stand far from that contour and watch matter trace loops that shrink into invisibility, can weigh the gravity that commands those loops, can measure the glow of gas that fails to keep itself from falling. Yet the place itself refuses portraiture except as absence with a circumference. The mind arrives at this limit and listens, as if waiting for a word that geometry cannot pronounce. Standing at such an edge is not a physical act, It is a posture of thought. The eye that looks for a surface finds only a horizon that is not a thing but a rule. The hand that seeks texture closes on vacuum shaped by gravity into a funnel where every path points down. The heart that wants a villain meets an indifference as perfect as math. Terror arises from that perfection. A region exists where the narrative breaks into two voices that never meet. One that continues to fall through ordinary space and time, another that watches from far outside and writes a log of light that grows slower and redder until the ink turns invisible. Both voices are true within their frames. Neither can correct the other. The line is called an event horizon because it partitions events into those that can be reported and those that cannot. This partition is not cruelty. It is bookkeeping. The world needs consistency more than it needs comfort, and this boundary keeps causality honest. If light could carry messages back out, the interior would be a room full of paradoxes, a place where paths could double back and rewrite outcomes that were already witnessed. Nature avoids that confusion by insisting on a direction that cannot be reversed. The word for that insistence is gravity, and the form it takes here is total. The boundary produces consequences that feel like parables. It shapes time for those near it. It sculpts the appearance of nearby matter. It focuses light into rings that circle an absence. It turns rotation into power by letting space itself spin and time magnetic fields into ropes that lift energy outward. It writes its temperature into near zero glow, so faint today that no eye can read it, yet real enough to speak a promise about how any store of mass will one day return to the emptiness it once borrowed from. The boundary is not a fence, it is a grammar, and the cosmos chooses to speak in its sentences wherever concentration pushes too far. The mind resists because minds were trained on surfaces that yield to touch. A rock has hardness, a flame has heat, a sea has waves that can be counted with a hand in the water. The horizon offers none of this. It is a place where a coordinate becomes a verdict. It tells light that direction has lost one of its meanings. It tells clocks that their ticks will never again be shared with distant partners. For those who want nature to be made only of objects, this boundary is a rebuke. It reminds that geometry itself is a player, that fields can be real without being things, that a rule can be a presence when nothing else remains. There is a solace hidden inside that rebuke. If gravity can shape space into a one-way membrane, then clarity survives even in extremes. Inside, a traveler feels no ridge at the crossing. Outside, the map of orbits and light allows predictions that reach extraordinary precision. The two stories coexist without contradiction because they have different jobs. One keeps faith with local experience, the other keeps faith with global accounting. The harmony between them, attentive and cold, is the only kindness the abyss offers. It is enough. It shows that even where ignorance is enforced, nonsense is not. The human impulse in front of such a limit is to turn outward and take inventory of what can be learned. A shadow can be drawn when baselines span a planet. A ring can be weighed with a ruler made of closure phases and careful priors. Knots in a jet can be followed as they march down a beam, their polarization turning like a compass that points to field lines too hot for metal. A merger can be heard by listening to jostled mirrors and subtracting the noise of Earth itself until a late whisper of space-time becomes a phrase with mass and spin inside. Each method is a way to stand at the event line without stepping across it, to find meaning in the glow and in the tremor, to respect the partition and still learn lavishly. What this edge offers most is perspective. It shrinks pride, not by humiliation, but by proportion. Hopes and fears are human and finite, but the rules here refuse to bend for any wish. They accept offerings only in the currency of mass and momentum, only in the units of field, strength, and curvature. Work is purified when measured against that indifference. Explanations become tight. Flowery language falls away. What remains are statements that survive being turned into numbers. The numbers endure because the geometry that birthed them does not care what one feels about it. In that honesty, wonder thickens to something steadier. Beauty is not a decoration on these rules. It is a symptom that the structure is spare and complete. A curve can be named and plotted. A horizon radius can be expressed in a single power of mass. A ring diameter, measured in micro-arc seconds, can return a value for a gravity that would flatten any laboratory. Then, as the breath taken by these facts completes, imagination resumes its role on a foundation that will not break. Hypotheses about seeds and storms, about winds that eat their own light, about pairs that become singles and write a new frequency into space, all gain or lose by how they seat themselves within this frame. The Edge teaches humility by making speculation accountable. Standing at the event line, thought can practice a kind of ethics. Not the ethics of choice, but the ethics of attention. Careful seeing is a moral in science, because truth has difficulty surviving in haste. The horizon rewards patience. It punishes careless inference. It invites techniques that double-check themselves by inventing challenges before they publish claims. The culture shaped by these demands is one of shared skepticism and shared wonder when skepticism fails to dismantle a result. In that way, the boundary between knowable and unknowable becomes a teacher. It trains minds not to pretend, to let the unknown stay unclaimed until a signal is ready. For the individual, the lesson settles into a quieter register. Life takes place far from any abyss of this kind, yet the principle scales down. There are limits that cannot be breached, facts about mortality and memory that no cleverness rescinds. Accepting those limits does not kill curiosity. It refines it. It aligns effort with what can actually be changed, and it leaves room for awe where mystery remains inviolable. The event line in thought is marked by the willingness to stop where knowledge becomes assertion, to say this much is sure and this other part is possibility, and this last part is darkness that has not yet learned our words. A black hole is not a symbol, it is a solution. Yet symbols grow around it because human minds grow symbols wherever rules feel enormous. The most useful of those symbols is a reminder that reality is under no obligation to be warm. It must only be consistent. That consistency, once loved for itself, becomes a source of meaning deeper than comfort. A cosmos that holds to its laws, even when those laws produce a silence deeper than any the ear can tolerate, is a cosmos that can be trusted. On that trust, minds can build narratives that respect what is and still reach for what might be. So the event line is both a limit and a blessing. It sets the stage for inquiry that never finishes and ensures that some parts of the stage will always be hidden. It protects causality from vanity. It turns rotation into light, it turns fall into heat, it turns union into music that travels through the bones of space. It asks for no allegiance, offers no truce, and keeps no score beyond those conserved in its arithmetic. The terror that first gathered here softens into reverence. The unknown does not shrink, the known does not inflate. They sit together, divided by a line with no thickness, and the mind learns to bow to both. Night leans across the dome and makes a single pupil of the world. Arrays go quiet, hard drives cool, clocks keep their private pulse. In that pause, the images seen and the songs heard gather into a stillness that is not empty. A ring of fire around a circle of absence rests behind the eyes. A curve on a screen, thin as breath and shaped like a rising heart, hums in memory. A jet braided by fields threads the dark like a thought that refuses to scatter. Figures remain on paper, clean and small, while the sky that gave them those values stretches without edge. There is work enough for lifetimes in the leftovers of this night. More baselines to add, more mirrors to calm, more pulsars to count, more algorithms to teach humility. Yet the richest yield is a habit, to look long without deciding too quickly, to let terror be a teacher that trims language to what can be proved, to let wonder be a companion that keeps courage steady when the known runs out. The abyss asks for this patience, and repays it with clarity that has no rival. If the future grows thin and quiet, if galaxies sleep and stars forget to form, the rules will remain, exact and indifferent, beautiful because they do not change. The largest black holes will keep their vigil until nothing is left to hold. Then, light will inherit the ledger. Until that age arrives, 100 generations can turn their faces to the event line and learn, not how to cross it, but how to stand near and listen. The lesson is simple and inexhaustible. Reality keeps its word.